Welcome to this course on data structures and algorithms. In this course, we will learn about some of the commonly used algorithms and data structures. We will start by learning about how to analyze algorithms, then move on to talking about arrays, which is an inbuilt data structure in most of the programming languages. Then we will learn some simple sorting algorithms like bubble sort, selection sort, and insertion sort. Then we'll talk about linked list and few different types of linked list like singly linked list or a doubly linked list. We'll also talk about stacks and queues before moving on to recursion. There are some more ways to sort data like counting sort, quick sort, and Redix sort, etc. So we'll learn about that. Finally, we learn about binary search trees, hash tables, and heaps. In this course, we will be using the Java programming language to write code to implement these various data structures and algorithms. Now, we'll not get very theoretical in this course, and the purpose of this course is mostly to understand data structures and algorithms. Let's start by looking at the definition of an algorithm. In the introduction to the algorithms book, the authors say that an algorithm is a way to solve a well-specified computational problem. Similarly, Donald Knuth has described an algorithm to be a finite set of rules that give a sequence of operations for solving a specific type of problem. For example, the recipe to make tea can be considered as an algorithm. You can follow these exact sequence of operations, and once you are done, you can have a cup of tea ready. In mathematical texts, one of the earliest algorithms is to find the greatest common divisor of two numbers, which is due to Euclid, who lived in Alexandria in about 300 BC. This algorithm is very simple. Let's say there are two positive numbers m and n. Now, to find the GCD of these two numbers, we first divide m by n, and let's say that the remainder is r. If this remainder r is 0, we are done, and the value of GCD is n. But if r is not 0, we set m equal to n and n equal to r, and then start with step 1. So as you can see, this is a recursive algorithm because it calls itself over and over. You can try this algorithm using a pen and paper with a few values just to ensure its correctness and get a feel of how it works. Another interesting problem that we study is the problem of sorting data. Sorting is so common to computers that we hardly realize if it is explicitly happening anywhere. But most of the data that you see on your computer, whether it is from some website or list of files in a directory, it's all sorted in some way. Now, we are intelligent beings and we sometimes do things intuitively without caring for the steps that are involved in doing a task. For example, for making tea, you don't say that, well, boil some water and milk and don't forget to put the tea bag and the sugar, and when you start making it, you'll figure it out. Well, most people may be able to make tea just by listening to that, but that's not an algorithm. It must be an exact sequence of well-defined instructions. So in that light, let's consider this problem of sorting these numbered balls according to the ascending order of numbers printed on them. Each of the ball is kept in a bin, and there is one empty bin which you can make use of. But there are some rules that you must follow. You can only pick one ball at a time. That is, at no point of time you will have more than one ball in hand. So this means that before picking up another ball, you must drop that already held ball in an empty bin, which is basically the same as rule 1. Now, this is not really a rule, but you may want to start from one side and move towards one direction. So let's say we start from the leftmost bin and move to the right to see what numbers are on the other balls. You can use a stick to keep track of the sorted part. Now I want you to think about how would you sort these cue balls given these set of rules. And as a hint, you can compare the numbers on the balls in the first two bins, and if the number on the ball on the right, which is 2, is less than that on the left, we can exchange the balls using the extra bin, which means that we pick ball 2 up and drop it into the extra bin, then move the ball with 10 to the empty position, and then move the ball with number 2 back into the empty bin. And this needs to be done over and over. So now you can try to think, how does this way sorts the cue balls? So as suggested, let's follow this process and see how it helps us sort the cue balls. So we compare the first two cue balls in the bin. Now 2 is less than 10, so we swap them using the extra bin provided. Then we move to the right by 1 bin. So we compare 10 and 8. Well, 8 is smaller than 10, so we do the swap. Then we move to the right by 1 bin again, and we keep doing that until we reach the last bin. And now if you notice, the ball having the largest number is in the rightmost bin, isn't it? And this should have been because every time we compare, the ball with the larger number moved to the right. So this way of sorting is known as the bubble sort algorithm, because in each pass the largest number kind of bubbles to one side. So we can keep a pointer here or a stick to keep track of the sorted part. Because the largest number has reached the rightmost bin, we can consider that part as sorted, right? Now we again start from the leftmost bin and compare the adjacent balls in the first and second bins. Now 8 is greater than 2, so we don't do anything, alright? We don't need to swap the balls now. And we just move to the right by 1 bin. Now we compare 8 and 6. And 8 is greater than 6, so we do the swapping. And we keep repeating this process until we reach the last bin of the unsorted part. Now we don't need to consider the last bin containing the ball with number 10 because that is already the largest. So now the second largest number 8 is at the second last position. So we can move our pointer here to keep track of the sorted part. And we keep repeating this process over and over until all the cue balls are sorted. Which means that the pointer has come to the first position. So this was the bubble sort algorithm in action that you just saw. Let's understand, why do we need to learn data structures and algorithms as programmers? When we solve programming problems, we would like to know, at least at a high level, how much time would our algorithm take to solve the problem? Does it take a few milliseconds, a few minutes, or a few days? Because having an estimate of time can help you decide how to break down your problem in relevant pieces or smaller problems. It may also help us decide on hardware requirements for solving a problem. For example, if we know that executing or running an algorithm on a certain CPU takes, say, 1 hour, we can use a more powerful CPU to reduce the time to a few minutes. Or we can think of breaking the problem and distributing it to many smaller CPUs, so they can execute a smaller problem parallelly and we get our results in a few minutes. Understanding algorithms also help us know if a particular algorithm is feasible as opposed to it being impossible to do the job. For example, if you are asked to sort a billion items based on some criteria in say 1 second, you would like to know if it is even possible to do it at all. And of course, improvement is a never-ending process. We would like to improve our existing algorithms, just like car manufacturers constantly work to raise the bar and want to make faster cars, even though it may seem like, well, what is the need? But that's probably how human civilization grows. We keep improving. We want to keep improving. Now, data structures are studied in context of algorithms. Data structures in computers are ways in which we store data. If we just store the data without doing anything with it, well, it doesn't really mean much. But particular ways of storing the data may help in faster access or faster saving of the data. For example, think about this. In a library, what will be easier to reach to a book? If they are kept like they are in their racks, or if they are put up as huge piles? What if you find your book at the bottom of the pile? Will it be easy to take it out? Or even within the racks, if the books are kept in some order or they are kept completely randomly. So the way we choose to keep the books may make it easy finding a book or easy keeping a book back in its place. In the same way, different types of data structures are used, which may make sorting of items faster or finding an item faster and so on. So we choose a particular data structure in our program depending on which of the operation is more frequently used or which operation we would like to be faster than the others. Now, how do we prove whether our algorithm is correct? Well, formal proofs require mathematical reasoning. Like we start with listing the statement to be proven, then any assumptions that we may be making, and then we start from some lemmas and theorems, and using a chain of reasoning and assumptions, we would reach the statement to be proven. Proofs could also be done in the reverse order. That is, starting from the statement to be proven, we try to reach some theorem or lemma. But in this course, we will not be very rigorous with proofs. At least we will not indulge in mathematical rigor. Rather, we will use some high-level logical reasoning to make sure that the algorithm is correct. One way to check if an algorithm is correct is to see if it is incorrect. And checking the incorrectness need not be rigorous. All we need to do is to show that it does not work for some set of data. And as heuristics, when considering such data, you may want to select a small set, especially the borderline cases. The main focus of this course is to help you easily understand data structures and algorithms. So we have used lots of animation in the video lectures, and then there are quizzes in between video lectures to help crystallize what you learned. I hope that you enjoy this course. In this chapter, we'll talk about how to analyze algorithms, that is, figure out how good they are. Now, this is slightly mathematical and theoretical, and many people don't get it in the first shot. So what I suggest is that you watch it at least once now, just to understand the terminology, because it will be used in later chapters. And then when you have seen some algorithms and written some code yourself, you may revisit this chapter later, alright? And in this chapter, we'll deal with the big O notation. When we talk about algorithms, there are two kinds of consideration that may be worth thinking about. How much space does it take to store data in memory to execute the algorithm? And how much time does it take for an algorithm to run? The first is said to be dealing with the space complexity of an algorithm, while the second one is said to deal with the time complexity of the algorithm. Now that RAM and memory in general is really cheap, we don't care so much about the storage of data, or we don't really bother how much space will be consumed to store the data. So when we talk about analyzing an algorithm, we mostly worry about its time complexity. That is, we would like to know how much time does an algorithm take. So that's what we'll focus on in this chapter. But how do we measure time for an algorithm? I mean, the same algorithm running for the same input will take different times when running on different kinds of machines, right? Or even if they are running on the same machine but in different environments, where the CPU may get hotter and hence slower in one case cannot be ignored. For example, what if the air conditioning where the machine was kept was not so good? So it would be really hard to talk about some absolute time that an algorithm may take to run. Now think about this. What if we wanted to find the best way to go from home to office or college? In terms of time, one may argue that it depends if someone who runs fast is running, or a small child is walking, or one is going by a car, or whatever. So the time will be different for who and how are they traveling. And even for the same person with the same transportation, the times could be different for different days depending on the traffic conditions probably. So can we not talk about the time in terms of the number of steps in walking, assuming the step size to be uniform? That is, can we not say that the best path to take is the one which has the smallest number of steps? That would be one step to abstract out or remove the complexity involving the environmental factors, or who or how are they traveling, right? So we choose a similar approach in studying the time complexity of an algorithm. So the first step is to talk about the running time of an algorithm in terms of the size of the input data. But even this doesn't quite work, because the same algorithm running on the same machine over the same set of input data will not really take exactly the same time in two different runs. Now, one thing to note here is that an algorithm working over a small number of elements will take lesser time than when it works over a larger number of elements. That is, say if an algorithm takes say 1 millisecond to work with 5 data items, it may take about 2 milliseconds or 4 milliseconds to work with 11 data items. So when we study time complexity of an algorithm, we essentially want to understand or know how the time of an algorithm varies with the size of the input data. That is, we would like to know what is called as the order of growth of an algorithm with the size of input data. Now, what does it mean? Let's say there are two algorithms to do something useful, say sorting data. And both the algorithms take 10 milliseconds to sort 100 items, alright? And then we would like to know how does the running time varies with some other input sizes. And then we are talking about the growth of time or the order of time. By the way, in actual runs, the time need not be exactly the same as shown. But we are more worried about, well, approximately this is how it should vary. By the way, we are using such small input data sizes, but in reality, when we talk about the order of growth, we usually mean it in terms of very large numbers. But I just use the small numbers so that you can understand the basic idea behind it. So in the data shown here, algorithm 1 can be said to have a linear growth of time, while algorithm 2 can be said to have a quadratic growth of time. So if we were comparing these two algorithms, or if we had to choose between these two algorithms, we will most likely pick algorithm 1 for our task. So in terms of time complexity, we say that algorithm 1 does better than algorithm 2. By the way, algorithm 2 may do better than algorithm 1 for say 50 data items. But we don't really bother about small data sizes. We talk about the order of growth for large enough data sizes, which is also called asymptotic analysis. We'll talk about that. Just try to understand it step by step. There are three main types of analysis when dealing with the time complexity of an algorithm: the worst case analysis, the best case analysis, and the average case analysis. Now talking about the best case running time of an algorithm is bogus. Okay, we usually don't care about it. We mostly deal with the worst case analysis. So for this course, that is what we'll stick to when talking about running times of an algorithm. The average case analysis is usually complex, so we will not really talk about it in this course. Sometimes average case analysis requires understanding and using some statistical methods also. To be able to analyze an algorithm, we need to make a few assumptions on how the operations are performed on the data. This is called the RAM model of computation. And we assume that we have infinite memory. That is, we don't really worry about memory constraints when analyzing algorithms. We assume that each operation that we do, whether it is a mathematical operation or any other, it takes 1 unit of time. Then each memory access step takes 1 unit of time. That is, when we want to read the data in a slot, that will take 1 step. Or if we move the data to another slot, that can be treated as 1 step and hence would take 1 unit time. We also do not care where the data is read from, whether it is being read from a real RAM or a hard disk drive or even from a network data stream. We assume that all the data is stored in the RAM and that is where we are accessing it from, or that we are moving the data around within the RAM itself. After making these assumptions, let's start to try and analyze the time complexity of the bubble sort algorithm, which you already know now from the previous chapter. Let's analyze the bubble sort algorithm in terms of the number of steps where each step is either some operation or memory access. And as already said, each of such step takes a unit time. Consider an array like the one shown here. Because we are doing the worst case analysis, we have used an array that is reverse sorted so that the algorithm has to do the most number of steps possible to sort this array in ascending order. Okay. That is, we will get the worst case performance of the bubble sort algorithm when the data is sorted the other way. And let's kind of draw a table to track the number of comparisons or swaps that may be involved in each step. So we start by comparing 12 and 8. So that is one comparison. And the swap is done in 3 memory access steps, alright? Because we used a temporary bin, or in a program, we will use a temporary variable to do the swap, alright? That is, 8 goes to the temporary variable, then 12 comes to the place of 8, and then 8 is moved to the first slot. So that's 3 memory access steps. Then we move and compare 12 and 7, which is one comparison step, and then we swap the numbers in 3 steps. So each time we are doing one comparison and 3 swaps, alright? So in all, in the first pass, we did 16 steps. And by the end of the first pass, the largest number, which is 12, has come to the rightmost slot. Similarly, we can find that in the second pass, we do 12 steps. Then in the third pass, we do 8 steps. And finally, in the last one, we do 4 steps. And the array is sorted. So for the whole sorting algorithm, we ended up doing 16 plus 12 plus 8 plus 4 steps for a data size of 5 elements, which were reverse sorted, alright, because we were doing the worst case analysis here. If the array was not reverse sorted, the number of steps will be lesser than what we have calculated here, alright. So in the worst case, we do these many steps for 5 elements. So we can take 4 as a common factor out of these numbers, so that the number of steps may be written as this. Again, this is for a data size of 5 elements. If there were n elements, intuition and a quick reasoning will tell us that the total number of steps may be written as this. The quantity in brackets is the sum of the first n minus 1 natural numbers, which are also called as triangle numbers, whose sum we already know is n into n minus 1 by 2. So this calculates to 2 into n minus 1. And this is a quadratic equation in n, which in general can be written in the form of Pn square plus Qn plus r, where P, Q and r are some constants. Let's look at the pseudocode for the bubble sort algorithm. Take some time to understand what this code is doing and then try to implement the algorithm in Java. Alright? So let's first understand it. In the outer for loop, we are varying I from a value of 0 all the way up to 2 less than the size of the array. Alright? And in the inner loop, j varies from 0 all the way up to the size of the array minus 2 minus I. By the way, unlike the pseudocode in many textbooks, I am using a 0 based index so that translating it to Java code is easier. So it is through this j index that we access the elements. So when I is 0, j starts from 0 and goes all the way up to the second last element. Then when I becomes 1 in the next iteration of the outer loop, j varies from 0 and goes up to the third last element of the array and so on. Thus for each outer iteration, the maximum value of j decreases by 1 because the value of I increases by 1. And at each step, when the value of j changes, we compare the element at the jth index and the next element at the j plus 1th index. And if the value on the left, which is at the j index, is greater than the value of the element at j plus 1 index, we swap them, alright? And just as I said earlier, looking at the pseudocode clearly tells us that the time for this algorithm varies as a quadratic function of the data size, which is the size of the array. Because when I was 0, j varies from 0 to n minus 2, assuming the size of array or length of the array to be n. So the number of operations, including comparisons and swaps, will be proportional to n minus 1, right? Because 0 is also inclusive in j. Then when I becomes 1, j varies from 0 to n minus 3, so that the number of operations are proportional to n minus 2, and so on, until I becomes n minus 2, in which case j starts from a value of 0 and ends up doing only one comparison and 3 swaps. So the number of operations is now proportional to 1. So the total number of operations for the algorithm will be proportional to the sum of all the elements in the outermost column, which we already know is the sum of the first n minus 1 natural numbers. So we can say that the time taken by the algorithm is proportional to some quadratic function of n, which is the data size. Now we come to the math of time complexity. To understand time complexity in a form of very simple expression, computer scientists define the big O notation, which is one of the many other notations dealing with time complexity, like the theta notation, the small o notation and all. But in this course, of course, we'll only deal with the big O notation. Let's say that the order of time that we found for our algorithm is a quadratic function in n as displayed here through this graph. And our job is to find the upper bound for this function Tn, alright? Now consider a function c1n square, and here c1 is so chosen that this function never overtakes the function Tn. But then we can choose another constant c2 such that c2n square is always greater than or equal to Tn for all values of n greater than n naught. Can you see that? Now we can say that c2n square is an upper bound of Tn, because after some value of n, c2n square will always be greater than Tn no matter what. But there may be many constants, actually infinite number of constants, that may be chosen such that the function that constant times n squared becomes the upper bound of the function Tn. So we need a new definition to be precise. Mathematics is about defining things precisely and without ambiguity, alright? So we define what is known as the big O of a function. And listen carefully. Pause the video later and try to understand what we mean by it, okay? So the big O of n square is a set of all the functions, okay? Remember, big O is a set of functions. So big O of n square is a set of all those functions fn such that for some positive constants c and n naught, cn square will be greater than or equal to the function fn for all n greater than or equal to n naught. That is, after some point n naught, cn square will always be greater than fn. In general, the big O of a function gn is defined like this. It is a set of all the functions fn such that for some positive constants c and n naught, c times gn will be greater than or equal to fn for all n greater than or equal to n naught. This is exactly the same definition as we saw above, just that the function n square has been replaced by a general function gn. So this definition just gives us an idea of an upper bound and not how tight the upper bound is, okay? We can choose some large constants c and n naught and show that the definition holds. Let's see a few examples to understand what the big O really means. Here we have this function 5n square plus 6. Does it belong to the set big O of n square? Well, if it does, then we must find some values of c and n naught such that cn square becomes greater than or equal to 5n square plus 6 for all n greater than or equal to n naught. So we can choose c as 6 and n naught as 3, and you can see that 6n square will be greater than 5n square plus 6 for all values of n greater than or equal to 3. Right? By the way, we can choose a different combination of c and n naught, alright? For example, we can choose c as 5.1. And now n naught must be at least 8 because for values less than that, 5.1 n square will not be greater than 5n square plus 6. So we can have infinite number of combinations and we don't really have to tell which is the best of the lot or which combination makes the bound tight. We just need to show that there is such a combination and we are done. So that's very easy. What about this function? Does 5n plus 6 belong to the set of functions represented by big O of n square? Well, yes. Going by the definition, we can see that if we choose a value of c as 11 and n naught as 1, we will get 11n square to be greater than or equal to 5n plus 6 for all values of n greater than or equal to 1. But we don't really worry about this kind of relationship because we would like to rather say that the function 5n plus 6 belongs to the big O of n, alright? What about this function? Can we say that this belongs to big O of n square? Well, no, because we will not be able to find positive constants c and n naught for which cn square will become greater than the n cubed polynomial function. Now, this is a little mathematically involving, so I suggest that you go through it once and may want to come back to it later to understand it again after you are done with implementing a few algorithms. In general, for a polynomial function, we can say that this function belongs to the big O of n raised to the power of m. That is, we just consider the highest power of n without worrying about the constant am. Now, this order of functions is worth remembering, alright? Because we'll usually talk about algorithms saying that it takes n log n for such operation and it is better than n square algorithms and things like that. So if some algorithm takes big O of log n time, then it is very fast, it is very good. Actually, constant time algorithms are the best ones. That is the best you could get. But apart from them, log n is quite good. Now because square root of n is greater than log n, hence root n algorithms are not as good as log n algorithms. By the way, we usually don't say big O of the function. We can just say root n algorithm or n log n algorithm, and it is implicit that we are talking about the time complexity in terms of the big O notation. Then come the linear time algorithms, which take time proportional to n, the size of the input. Then n log n algorithms, then n squared algorithms, n cubed, 2 raised to the power of n, which is exponential time algorithm, and then n factorial type algorithms. Now exponential time or factorial time algorithms are not good algorithms. And these are special type of problems which we will not deal with in this course. We'll only talk about problems which take polynomial time to solve. But even polynomial time algorithms are considered bad if they take n cubed or more time. They are only used if there is no better alternative available. But as you will see in this course, we will mostly deal with algorithms which can be done within n squared time, alright? Let's see what the notation means and how it is used for getting a sense of how fast an algorithm is. Suppose we have an array of integers, say of size 6. If we want to access the element at index 4, it will take some time. Let's say it takes 10 milliseconds. By the way, array elements are accessed by using index as an offset from the first element. So it's really fast. So now if we have an array of 100 elements and we want to access the 99th element, how much time does it take? Well, it will still take about 10 milliseconds. So here accessing the array element using an index does not depend on the size of the input. So we say that accessing array elements through their indices is a constant time operation which we represent as big O of 1. Then let's take another example. We have an unordered array, that is all the elements of an array are in random order, neither ascending nor descending. If we were to search an element, what is the worst case situation? Well, if the data in the array is random, we will have to start searching from one side, element by element, alright? So let's say we want to search for the element 9 and we start our search from the first element of the array. In the worst case, 9 may not be present in the array. So we will have to go through all the elements of the array until we find it or it does not exist. Now accessing each element takes some time. So let's say for going through 5 elements, it takes 50 milliseconds. So if we were searching for say 20 in an array which is double the size, that is it has 10 elements and 20 doesn't exist in this array, which is the worst case, or maybe 20 is the last element of the array, then the time to go through all the elements will take about 100 milliseconds. Because it takes say 10 milliseconds to access each element and do the equality check. So in the second case, the number of elements have doubled. By the way, it will not be exactly 100 milliseconds. We are just talking about the order of time or how it grows with the size of the input data. So this kind of search algorithm is said to be a linear time algorithm. Or we say that searching for an element in case of an unsorted array takes O(n) time. Alright? Let's revisit the bubble sort algorithm, which you already understand well enough by now. If you recall, we said that the time taken by the algorithm was proportional to a quadratic function in n, which is an n squared algorithm, or it is the big O of n squared algorithm. And usually, if we have a loop inside a loop, like for bubble sort, there is a for loop inside another for loop. we usually get n square time complexity. If we have one loop inside of the other, which is inside another loop, that usually means n cubed time complexity. By now, you should have a feel of what we mean by the big O notation, and you should be able to talk about algorithms in terms of the big O of a function as far as the time complexity is concerned. The quizzes will help you understand the idea of big O better, so make sure that you try them all before moving on to the next chapter. There are three commonly used n-square algorithms for sorting. You already know and should have implemented the bubble sort algorithm. In this chapter, we will learn two more sorting algorithms which take n square time. The first one is the selection sort and the other is called insertion sort. So let's start by understanding what the selection sort algorithm is. Let's consider the cue balls in a bin again. We have an empty bin which we can make use of, and again we can use a cue stick to keep track of item or items if we want to. In the selection sort algorithm, what we do is that we search for the smallest element and swap it with the item in the first bin, which is the leftmost bin. So the first element becomes sorted because that contains the ball with the smallest number. So this was iteration 1. In the next iteration, we do exactly the same thing with the remaining array. That is, starting from the second position, we search for the cue ball with the smallest number out of the remaining ones, and when we find that, we swap it with the ball in the second bin. So now the ball with the next smallest number is in the second bin. So the first two bins are sorted. And we keep repeating this process until all the balls are sorted. So it is called the selection sort algorithm because every time we select the smallest number and then swap it with the item in the relevant bin. So if we have an array of numbers, we go through all the elements to find the minimum and then exchange it with the first array element. So that this is how the array looks like, with the first element as sorted. Then from the remaining elements, that is starting from the second array element, we find the minimum and then exchange it with the second element of the array. So now the first two elements are sorted, and we keep doing this until the whole array is sorted. Let's look at the pseudocode for the selection sort algorithm. What we are doing with the selection sort algorithm is that we are swapping the smallest number with the first element, then moving to the second element and swapping the next largest with the second element, and so on. So we start from the first element, which is the 0th index, and go all the way up to the second last element, whose index is equal to 2 less than the length of the array. So the index I will keep track of the element from which the minimum needs to be exchanged, alright? Then we need to find the index containing the minimum element. So we can initialize it with I, because in each iteration the element at I may be the minimum. As you can see, we don't care about elements before the ith index, because they will all be sorted. After initializing the min index with I, we can loop through all the remaining elements of the array, starting from I plus 1th index, and see which of them is the minimum. So we write another loop going from index I plus 1 all the way up to the last element, and check if the element at the jth index is less than the element at the current min index, And if it is, we change the min index to j because the element at the jth index should be the minimum. After this inner for loop is over, the min index will be pointing to the element with the minimum value over the elements that this for loop went through. So all we need to do now is to exchange the element at the min index, which is the minimum element, and the element at the ith index. And we can just use a temporary variable to do that. All right. And as said earlier, the index values that we are using in the pseudocode is the same as what we use in real arrays, so that translating it to a Java program is not difficult at all. That is, we use a zero-based index even in our pseudocode. Now let's see one more n square time algorithm, which is the insertion sort algorithm. This algorithm is inspired by the way we usually arrange cards when we are playing a card game. A typical way to arrange the cards is we draw a card and then see if the number on the card is smaller than the topmost card in hand. So here we compare 10 with 5. And because 10 is greater than 5, we just put the 10 of diamond on top of 5 of diamond. Then we draw the next card from the pack. Let's say we get a 9 of diamonds now. We compare the number 9 with 10. 9 is smaller than 10, so we move the 10 of diamonds to make space for the new card. Then we compare 5 of diamonds with 9, and because 9 is greater than 5, we don't move any more cards and place 9 in the newly created space between 5 and 10. Then let's say we get an 8. We compare 8 and 10. 8 is smaller than 10, so we move 10 to the right to make space. Then we compare 8 and 9. 8 being smaller again, we move 9 to a right a little. Then we compare 8 and 5. 8 is greater than 5, so no need to move the 5 of diamonds, and we place the 8 of diamonds right between 5 and 9. So this approach is the essence of the insertion sort algorithm. And essentially, the cards that are in hand are always sorted. When we draw a new card, it is again placed in a position such that we have all the cards in the sorted order. Think about it and meditate on it if you have to before moving on. Let's use the cue ball example to see how we can apply this technique to sort the cue balls. So we start from the leftmost bin, and because right now we have only one ball, we have this part of the bin in the sorted order. And we keep all the bins covered just to be able to relate it with the idea of drawing a new unseen card from a pack. Alright? Then we remove the lid of the next bin. Now the number 2 is the new number which must be placed in the right bin such that all the balls in the open bins are sorted. And because 2 is less than 10, we move 2 to the extra bin or the temporary bin, then move 10 over to the right, and then place 2 in the empty bin. So now again the left part or the balls kept in the bins without lids are all sorted. Then we remove the next lid. We compare this new number with the rightmost number of the sorted array, which is 10. So 8 is less than 10, so we move 8 into the temporary bin and then shift 10 to the right bin. Then we compare 8 and 2. Now 8 is greater than 2, so we don't need to move items anymore, and we place 8 in the empty bin kept between 2 and 10. So this left part of the array is again sorted. Then we remove the next lid. And we keep following this approach until all the bins are sorted. Let's look at the pseudocode for this algorithm. Let's start with an array. And we need to go over all the elements of the array one by one, inserting the newly accessed element in its right place so that the already accessed part of the array remains sorted. So we must write a for loop, using which we can access each element of the array one by one. That is, we should be able to access elements from the 0th index up to the last index, which is given by 1 less than the size of the array. Here we represent the array with a capital letter A. The first thing we do is to save the element at index I into a variable, and let's call it current. So that even when we write over the index I, the element at I is saved in another variable and we are able to access it later. Then we start accessing the elements of the array starting from the previous index, which is I minus 1. Now we would like to compare the elements of the array one by one with the current element, going to the left to check if the current element is less than these elements. So we do this until either we have reached the leftmost end of the array or the elements at index j are greater than the current element. We can do this in a while loop. And as long as this condition is true, we keep shifting the element at index j to the right by 1. So here 12 shifts to the right. Then we reduce the value of j by 1 so that we can access the element 8. So 8 is also greater than 7. So we move 8 to the right. Then again reduce the value of j by 1 because this is happening in a while loop, right? So now the index j is pointing to element 5, and because 5 is less than 7, hence the while loop ends. And what we need to do is to put the current, which is 7, in the array slot with index j plus 1, because j after the while loop was executed was pointing to the element 5. Alright. So this was the pseudocode for the insertion sort algorithm, and again I suggest that you spend some time thinking about it. Alright. Let's compare the three sorting algorithms which we have studied. All of these take order of n square time in the worst case. But there are still few other differences between them. Out of these three, bubble sort is the most inefficient algorithm. Practically, it is never used in real programs and it's just taught so that, well, we have one more thing to study about. Well, I'm just kidding, okay? Actually, it is a very simple algorithm to understand, so it is studied as a first sorting algorithm. Selection sort is a little better algorithm than bubble sort, and one interesting thing about selection sort is that its running time is independent of the ordering of elements, because we need to perform the same number of steps to search for the smallest element and then exchange it with the element at the right slot. So it requires the same number of steps in the exchange as well as the same number of steps in the selection of minimum. So it doesn't quite matter if the array is nearly sorted or not. Insertion sort is a very versatile algorithm because not only is it quite efficient for a small number of items in an array or list, but it can also be used along with other sorting algorithms to make it more efficient. For example, insertion sort is usually used in the shell sort algorithm, which we will study in a later chapter. Insertion sort is quite fast when the array or list is nearly sorted, because the number of steps in shifting the items to create the slot for the new item are reduced significantly. Actually, for nearly sorted lists, the order of time is almost linear. So practically speaking, if you have a small number of items to sort, go with insertion sort. Apart from the time complexity of an algorithm and checking if the sorting is in place or not, we also consider whether an algorithm is stable or not. So what does that mean? Well, it's a small thing. Consider an unsorted array with two elements having the same value 5. So I have marked them as 5 and 5 prime just to be able to distinguish the two numbers, although the numbers are the same, of course. Now after the sorting is done on the array, if the result of sort is this, we call it a stable sort, while if the elements are arranged like this, we call this an unstable sort. And what is the difference? Well, the difference is that in case of a stable sort, the order of the elements in which they occur in a list or array is maintained even after the sort. Like in this case, 5 came before 5 prime in the original array, so that order is still maintained here. 5 still comes before 5 prime. Whereas if you look at the unstable sort, the order of equal elements has been changed, so that 5 prime comes before 5. That's it. So if you wrote your insertion sort algorithm like this, where we are moving the elements based on strictly greater than relationship, then if the element on the left is equal, it will not be moved. So for equal elements which were at the left will remain on the left side. This will make the sort stable. But if we made this slight change here and write greater than or equal to, the sort will become unstable, because now even if the element is equal to the current one, it will be moved to the right. And then the current element, which was originally on the right side, will come to the left. So be careful with stable versus unstable sorting, because at the face of it, although it doesn't seem to make much of a difference, but this example will help understand why stable sorts may be better. Let's say that on a web page, some data is displayed in the form of a table. And right now, the data is not sorted according to any of the columns shown. Then let's say we click on the age column, which sorts the data according to the age. So that this is how the page may be showing the data now, alright? After this, let's say that the user wants to sort the data by name. So they click on the name column. Now there are two ways that the data may get sorted. Because the name Nancy Cooper appears twice, when we sort it, the sort may be stable or unstable. If it is stable, then because we had earlier sorted by age, hence Nancy with age 24 should appear before Nancy with age 28, and that is what we would like to see on the page probably. But if the sort was unstable, Nancy with age 28 comes before Nancy with age 24, which sort of messes up with the previous age-based sorting a little. So yeah, stable sorts do have some uses. So we would ideally want sorts to be stable, because for cases where it does not matter, stable sorts will not bring any harm, and where it does matter, they should be used anyways. After learning about these basic sorting algorithms, let's see how can we search for an item in an array. And let's understand the worst case time complexity of searching for an item in an array. Let's start with an unordered array, which is basically the one in which the elements of the array are unsorted. They can be in any random order. Now, accessing an array element through its index is very fast, alright? Because when we reference an array, we basically have the address of the first element. And going to any other element is very fast. Just by adding the index number as an offset to the first element's address, we get the new address and the element can be accessed through that. So accessing array elements like this does not really depend on the size of the array. And we say that accessing array elements through their index is a constant time operation, which we write as O1, alright? But what if we want to search for an element without knowing its index? For example, what if we want to find the number 8? What would be the worst case time complexity of this operation? Think about it. If the elements of the array are not in any particular order, we will have no idea where 8 is present. It may be at the 0th index or the last index, who knows? So the best strategy would be to start from one side, let's say starting from the 0th index. We access the elements one by one and see if the element at that index is equal to what we are looking for. And if the element is found, maybe we return the index of that element. In the worst case, what may happen? The element is not there in the array at all, or probably it is the last element of the array, which means that we will have to go through all the array elements before we can figure that out, right? So that means in the worst case, it will take time proportional to the size of the array to be able to find the element or say, well, it's not there. It is just like the case where you go into a library to find your book and there is this large bookshelf with a whole lot of books in it. And unfortunately, someone has messed it up and the books are not kept in any order. So if you have to find your book, let's say we are looking for the book Growing Through Divorce. So we start from the left and keep checking each book one by one until we get to the book we are looking for. So we say that finding an element in an unordered array takes order of n time in the worst case. And what about deleting an item? Well, delete also takes order of n time because we should first find the item and then delete it, alright? Let's see how to find an element in case of an ordered array now. Ordered arrays are those in which all the elements are sorted, either in ascending or descending order. So let's assume for our example that all the items are sorted in ascending order. In the last part, we saw how to find items when the data is completely random. Now that we know that items are ordered, can we do better than order of n time? Because now we have some more information about the data. Imagine that you have to go to a library and you have to find a book by its title on a really long bookshelf. If the books were kept in a completely random order, you will have to start from one end and keep going linearly one book at a time until you find the book, or say the book is not kept on that shelf. But if you know that the books are kept according to the alphabetical order of their titles, can you search for the book faster? Pause the video here and think about how can you find the book faster. Let's say that we have this bookshelf and imagine that this is a really long bookshelf with lots of books. And let's say we want to find the book Life of Pi. Of course, if there are few books, you would quickly glance through all of them to find it without even realizing. So imagine that there are lots of books and the bookshelf is really very long, say a 30-yard long bookshelf, alright? Because they are ordered according to the title of the book, you can quickly walk a few steps ahead and check the title of the book in front of you. If the title of the book you are finding should alphabetically appear after this book, you walk a few steps ahead again and check the title of the book in front of you. Now, if your book's title must come before this book's, you walk back and check the title and then probably move ahead again until you find the book you are looking for. By the way, we also use our intuition to figure out how many steps should we move in the forward and the backward direction. But a computer is a very fast but quite a dumb machine. So it must be told exactly how many steps to move forward or backward. To find an element in an ordered array or an ordered list, we use a similar approach. So let's say we are supposed to find the number 60 in this sorted array. So we start from the midpoint of the array. That is, we find the middle index of the array. Now the array may have even number of elements, in which case we will not find the exact middle index of the array. So we can find the middle index as the max array index, which is 7, plus minimum array index, which is 0, and divide it by 2. And take the floor of the result to get an integer. because this division may give us a real number. So we get the number 3, which is the first index we look at. We check out what element is at that index and see if it is equal to the number we are searching for. In this case, 32 is less than 60. Hence, we are at least sure that if present, the number must be at the right side of the array. So we just ignore the elements which are at the left of the index 3. And now we need to find which index should we look at. So we again choose the middle index of the remaining part of the array which needs to be searched. And we can find this new index as the max index of the remaining array, which is of course 7, plus the minimum index of the remaining array, which is 3, and divide this by 2 to find the midpoint. And of course, this number may be a decimal number, hence we have to take the floor of it. And thus we get the new index again, which is 5. So we check the element at index 5, which is 55, which is less than 60. Hence, if present, the element must be on the right side. So we ignore the left half part of the array. And again find the new index using the same process. And this time the new index is 6. So we check out the element at 6, which is 60, and this is equal to the element that we are looking for. So we claim that the element is found at index 6. This type of search is called binary search, because every time we are reducing the search space by half, alright? Now this way of searching is very fast. So let's see the worst case time complexity of searching for an element through an ordered array. In the worst case, how many elements will remain in the array to be searched if the element is either found or not found? Well, every time we are reducing the search space by half, and in the worst case, we may have to keep searching until only one element is present in the search space, right? And when we check this element, the element to be searched might be equal to this element, so that the element is found, or it may not be equal, in which case the element to be searched does not exist in the array, alright? Make sure that you understand this part before proceeding. Now, in the first search step, how many elements do we have in the search space? Well, it's the whole array, right? So n elements, given that there are n elements in the array. If the element is not found, when we checked the middle element of the whole array, we go to the second step, in which case we ignore one half of the array depending on which side the element to be searched might be. So in the second step, the number of elements in the search space of the array is n by 2. Then in the third step, the number of elements will be n by 4 and so on, until we reach, say, the ith step. And in the worst case, there will be only one element of the array left to be looked at, right? Now, if we look at the pattern of how the number of elements are halved in the search space with each step, that is, in step 1 there are n elements, in the second there are n by 2, then n by 2 squared, then n by 2 cubed, and so on. So in the ith step following that pattern, there should be n by 2 raised to the power of I minus 1 elements. And of course, this is equal to 1 in the worst case, right? So now all we need to do is solve this equation and get the value of I in terms of n. So I is equal to 1 plus log base 2 of n, and I also happens to be the number of steps involved in completing the binary search. So we say that the worst case time complexity for finding an element in an ordered array or list is big O of log to the base 2 of n. Now log n algorithms are really fast algorithms, alright? And just to get an idea, take a look at this table. If there are 2 elements to be searched, log to the base 2 of n is 1. If there are about 1,000 items, log n is 10. So it takes about 10 or 11 steps to search for an item. For 1,000,000 items, it takes about 20 steps. And for 1,000,000,000,000 items, it just takes about 40 steps in the worst case to look for an item. So this is really fast algorithm, alright? Let's see how to insert and delete items in an ordered array and the time complexity involved in these operations. Let's say we want to insert this item 52 in the ordered array shown. Well, the thing is that even after inserting the item, the array should remain ordered, alright? So that means we must first find the slot where this new element goes. And understand that we are not really finding this item 52, alright? So we pretty much have to start in a linear fashion, starting from the left. And we keep checking for items at each index until we find the one which is greater than the item to be inserted, which is 52. So now we need to make space for that. So we need to move all the items over by one index until there is a empty slot for the new element. And then we copy the element in this empty slot, alright? So inserting an item takes order of n time because first we need to search for the slot going over all the elements linearly and then also move the items to make space for the new element, alright? Now, what about deleting an item from an ordered array? Well, to delete an item, we should first search for it. And that we already know takes order of log n time. But after we delete the item, we need to move the array elements so that the array remains compact. We cannot have missing elements in the array, alright? So the time for deleting is order of n because in the worst case, we may need to copy all the elements of the array over, which is the case when the first item was deleted. So the worst case time complexity for the delete operation in an ordered array is of the order of n, alright? Till now we have been dealing with arrays of integers as the only data type for the various algorithms that we talked about. Let's consider a circle class as shown here. This class has a radius member variable which is initialized through the constructor. What if we wanted to sort an array of circle type objects based on their radius value? How would you do that? Well, one approach is to write another sorting routine. So let's say in the insertion sorter class, we overload the sort method such that it takes either an array of integers as parameters or an array of circles as parameters, alright? But then for each new type like a circle, we need to keep writing different sort methods which do exactly the same thing, but the way we compare the objects is different. Well, Java provides a better way to handle this kind of situation. We can use what are called as generics and write code such that we don't have to rewrite the sort method for different types of objects. Now, this is more to do with Java than data structures and algorithms. So I'll not explain the use of generics here, but the relevant source code has been attached to this video in case you are interested in knowing how to use generics. In this chapter, we'll discuss the linked list data structure. We will learn what they are, how they are implemented, and what are the different types of commonly used linked lists. A linked list in simple terms is an ordered set of data elements such that each element contains a link to its successor. So a linked list contains data elements and each element points to the next element. And the last element of the sequence points to a null element. These data elements are called nodes. The linked list itself contains a reference to the first element of the list, which is called the head element. Now let's see what a node is. A node in a linked list can be thought of as divided into two parts. One part contains the data, and here data can be anything that we want to store. It may be of primitive type like int, double, etc. Or it can be an object reference which may point to some object. For example, if we were maintaining a linked list of, say, user objects, where the user represents a user of a system having fields like first name, last name, email ID, etc. The other part of the node holds the reference to the next node. That is, it points to the next node. And if it is the last element of the sequence, as I have already told you, it points to null. So this whole structure is called a linked list. And as mentioned earlier, the linked list object contains a reference only to the head element, not to any other element, okay? Although we can access any of these elements by starting from the head element and going to the next node from there. Now let's write some code to create a node. In your IDE, let's create a new package for this chapter. Now inside this package, let's create a new class and call it node. Now let's declare the member variables data and next node. So we write private int data and then private node next node. So here we are assuming that the data is going to be of int type. And as you can see, we have made these variables private. So to access these, we use getters. We write it like this. Now let's write a constructor for the node class like this. So our node class is complete and we can create objects from this class. Now let's turn our attention to a linked list. Getting back to the linked list, as you can see, it contains a reference to the head element. And that is the only reference we have in a linked list. Using this reference to the head element, we can perform tasks like adding nodes or deleting nodes, etc. So now let's see how we can implement a linked list. In your IDE and in the package for this chapter, create a new class and name it linked list. And the linked list just contains one node, which is the head element. So in its simplest form, a linked list is just this. Of course, we will need to add some methods to it, like one for inserting a new node or element, and that's what we'll see in the next lecture. Now, let's see how a new node is inserted in a linked list. As we have discussed earlier, the only reference we have in a linked list is that of the head element. And one of the common use cases is to insert a new node at the head, which means that the new node to be inserted becomes the head element of the linked list. Let's see what we mean by that. Here we have a linked list with a few nodes. We want to add 5 to this linked list. So we create a new node for it. To insert this node at the head of the linked list, we need to connect the next node reference of the new node to the existing head element of the linked list, and then make the head of the linked list point to the new node. And this order in which we connect the nodes is very important. For example, if we connect the head object reference of the linked list to point to the new node first, what do you think would happen? Think about it. Well, what will happen here is that the link to the existing head, which in this case is the node with value 1, will be lost, and hence all the existing elements of the linked list will not be accessible anymore. Because as we saw, we can access the elements only through the head element. So the order in which we connect the nodes is very important. So we first make the next node of the new node point to the existing head element of the list, alright? and then make the head of the list point to the new node. Now all the connections are maintained, and this is how the list would look like after we are done with inserting the new node at the head of the list. Note that inserting a new node at the head is a constant time operation. That is, it takes O1 time to insert a new node at the head, which means that it doesn't really depend on how long the linked list is or how many elements does the linked list contains, because we are always adding the new node at the head element. So there is no traversal of the nodes required here, right? Now let's write the code to implement this in the IDE. Open the linked list class that we created earlier, and now let's implement the insert at head method. So we write public void insert at head and pass the integer type parameter to be inserted. Now inside this, we first create a new node object and then make the next node of this new node object point to the current head, like shown here. Then we make the head of the linked list point to the new node object, making it the new head element. Now let's create a new class and name it linked list demo. We write a main method, and inside this we first create a new linked list object and name it list. Then we call the insert at head method on this list object and add the values 5, 10, 2, 12, 19 and 20 like this. Now to print the integers, we override the toString method in both the node and linked list classes. So in the node class, we override the toString method and return the data of the current node. Then in the linked list class, we do the same thing. Now here, we would like the string to print the data for all the nodes contained in the linked list, starting from the head element. So declare a variable called current, which points to the head. Then we use a while loop to go through all the nodes of the list till the current node points to a null. We get the string created from the node object and append it to the result variable and separate them by using a comma. Then we go to the next node. And finally, we return the result. Now let's get back to the linked list demo class and run the program. As you can see, all the integers held in the nodes are printed. So this is how we implement a linked list. Sometimes we may want to know the length or the size of the linked list. That is, how many elements are present in a linked list. So let's implement the length method in the linked list class. If there are no nodes in the linked list, that is, the linked list is empty, the length of the linked list will be 0, right? That's straightforward and easy. Now consider this linked list object. To find its length, we can start at the head element and keep a counter to count the number of nodes. And then we go through all the nodes of the linked list one by one till it reaches null. And whenever we move to the next node, we can increment the counter by 1. So in this example, the length of the linked list is found to be 6. So the length of a linked list is defined by the number of nodes that are present in the linked list. Now let's implement the length method in the linked list class. So let's write the length method. And inside this, we declare a variable called length and initialize it to 0. As we did earlier, we make the current node point to the head. and then use the while loop to traverse through all the nodes of the list. Now inside the loop, we increment the value of the length and move the current node to the next one. After the while loop is finished executing, we return the length. Now let's go to the linked list demo class and print the length of the linked list. Now let's run the program to make sure that it works fine. We have already seen how to insert a node at the head of a linked list. Now let's see how we can delete the head node from a linked list. Consider a linked list as shown here. The head node is to be deleted from the linked list. And how do we do that? Give it a thought, it is very simple. To delete the node at the head, all we need to do is to make the head reference of the linked list object point to the next node of the head object. So let's do that and see what happens. As you can see, there is no reference to the previous head. That is, no object reference points to it now. It is to be noted here that although this node may be pointing to the next node, but nothing points to it, and thus it is not connected to the linked list in any way and is ready for garbage collection. So it gets deleted. This is how we delete the head node from a linked list. Note that deleting a head node is also a constant time operation. That is, it takes order of 1 time. Now let's see how we can implement this. Let's go to the linked list class and write a method delete from head. All we have to do here is make the head reference point to the next node of the current head. Now let's go to the linked list demo class and call the delete from head method from here. And then let's print out the linked list object. Also, let's print the length of the linked list, which should be 5 now. Let's run the program. And as you can see, the new head is 19 and the length of the list is 5 because 1 node got deleted. Next, we'll talk about how to search for an item in a linked list. We have learned how to insert and delete a node at the head. Now let's see how we search for an item in a linked list. Now to search for an item in a linked list, we have to go through all the elements or the nodes of the list till we find the element we are searching for. Or it may so happen that the data we are searching for is not there in the list. But either ways, we have to traverse through all the elements of the list to find that out. Let's understand this with the help of an example. Consider we have a linked list as shown here and we are searching for some data item, say 12. So let's use an object reference which starts from the head element and moves through the elements one by one till it finds 12. As you can see, searching for an item in a linked list is a linear time operation. That is, in the worst case, it takes order of n time, right? Because if we increase the size of the linked list, the time to go through each item will also increase proportionally. Now, suppose we want to search for the data 15. Again, we move through all the elements one by one until we reach the null object, which is the end of the linked list. So the item 15 is not present in the list. But as you saw, we still had to move through all the elements. And this really is the worst case scenario, which we say it takes order of n time. Let's go to the linked list class and implement the find method. Now here we initialize the current node to the head element and we will use a while loop to go through all the nodes. And when the data is equal to the data held in the current node, we return that node, which will also break the while loop. And finally, if the whole loop is executed without the data being found, we just return null, which would mean that no node has been found to contain this data value. Let's go to the linked list demo class and try to search for 12 and print the result. Now let's run the program. And as you can see, 12 is printed, which is the node value. Now let's search for 15 and print the result. And this time null is printed because 15 is not there on the list. Now we'll talk about a second type of a linked list, which is called doubly ended linked list. As the name suggests, this type of a linked list has two ends. It has a head and a tail. The tail refers to the last element of the linked list. So in this type of a linked list, we have references to two elements, the head and the tail, unlike in case of a singly linked list in which we have a reference to the head element alone. In a doubly linked list, we can add and delete elements at both the ends, that is the head and the tail. Doubly linked lists are not very commonly used, so we'll not discuss them in depth here. Let's write the code to implement a doubly linked list now. Create a new class and name it doubly ended list. Now inside this, we first declare two member variables, head and tail, and both are of type node. In case of a doubly ended list, we can add a new element either at the head or at the tail. Okay. Adding to the head is quite similar to what we have already seen. So let's write the insert at tail method, which takes int type of data as parameter. And inside this method, we first create a new object of node type. Now suppose there are no elements in the list. We need to check for this condition. So we write that if the head is equal to null, the new node becomes the head. Then we write another if block of code to check if the tail is not equal to null. The new node becomes the current tail's next node, which makes it the new tail. And then we override the toString method like we did earlier. Now create another class and name it doubly ended list demo. Then in the main method, we create a new doubly ended list object and call it dlist. Now call the insert at tail method on this object that we created, and now print the result. Doubly ended lists are not commonly used, as I mentioned earlier, so we won't be discussing it any further. Now we will see how we can insert a new node in a sorted linked list in such a way that the list remains sorted even after inserting the node. But before we go to a sorted list, let's first consider the two cases where the new node becomes the head of the linked list. In the first case, we look at the empty linked list, where the head element is pointing to a null. Since there are no other elements, this new node becomes the head element of the linked list. In the second case, we look at a sorted linked list. We use a pointer and compare the head and the new node first. and we find that the head is bigger than the new node. So if the list is sorted and the head is bigger than the new node, and by that I mean the value contained in the head is bigger than the value contained in the new node, then this new node will become the new head to keep the list sorted. So the new node now starts pointing to the current head as its new node, and the linked list updates its head element to the new node. Now let's look at the general case of a sorted linked list, and let's find out the position where we can insert this node and keep the list sorted. What do we need to do? We must go through the elements one by one, starting from the head, and check between which two elements can this new node be inserted. So let's do that. First we compare 5 and 17, then we move to the next node and compare 7 and 17, and then 10 and 17, 15 and 17, 16 and 17, and finally 19 and 17. And because the current node has a value greater than the new node must be inserted before the current one, right? That is, it must be inserted between 16 and 19. But if you notice, now the current node is pointing to 19, and there is no way it can go back to node 16 because there is no back reference. We can only go forward to the next node in the linked list. So although we will be able to make the node 17 point to node 19, we cannot make node 16 point to node 17, alright? Because we don't have any way to go to node 16 from node 19. So this is the wrong way to insert the node. And what we need to do is this. If you notice, from any node in a linked list, we can access the next node because every node has a reference to its next node. So we can compare the new node to the next node of the current one, or the current node that we are pointing to. Let me show you what I mean. Right now the current node is pointing at 5. So we compare 7 and 17 from here. Since 7 is smaller than 17, we now move the pointer to 7. And we compare 10 and 17. Move the pointer again, and so on till the pointer is at 16. And now we compare 19 and 17. As 19 is greater than 17, we can be sure that 17 is to be inserted between 16 and 19. That is, 17 has to be inserted between the current node and the next node of the current node. So let's do that. So as a first step, we make the next node of the 17 point to the node 19, which can be accessed as current node dot next node because current node is at 16. And then the next node of the current node, which is 16, will point to the new node 17. So this is how we insert a new node in a sorted linked list. Now, what is the worst case time complexity for this operation? Well, it takes order of n time and is a linear time operation because in the worst case, it has to traverse through all the elements of the linked list and may have to add the new node at the end of the list. And that would be the worst case, right? Till now, we have seen and used a singly linked node. Now let's see a doubly linked node and understand what it is and how it works. A doubly linked node, just like a singly linked node, holds some data and points to its next node. But what is different in a doubly linked node is that it can also point to its previous node. So a doubly linked node points to its next as well as previous nodes, and thus we can move back and forth in a doubly linked node, unlike a singly linked one using which we could only move forward or the next nodes. Note that if you create a node object and don't initialize its reference, Java automatically makes it point to null objects. Now let's see how a doubly linked node is used to create a doubly linked list. As shown here, in a doubly linked list, every node points to its next 10 previous nodes. Now we want to insert a new element, say 8, at the head. Alright. So let's see the final state of our doubly linked list after we have inserted the new node 8 at the head. And this will help us visualize which references to change or update in the list to be able to add this new node. So as you can see from the final state of the list, we need to make the next node of the new node, which is 8, point to node 5, which is the current head of the linked list. That is, in our Java code, we can say that node.nextNode is equal to linkedList.head. Alright. Next, as you can see, we have to make the previous node of 5 point to node 8, right? And node 5 is still the current head of the linked list. And right now its previous node is pointing to null. And we need to make it point to node 8. So in our program we can say that linked list dot current head dot previous node is equal to the new node which is being inserted in the list. And finally, there is one more reference to be updated. The new node has to become the head node of the list. So that's easy to do. And this is how we insert a new element at the head of the doubly linked list. Now let's implement this in Java. And I want you to pause the video here and try to implement it yourself before seeing the solution. Let us first create a new class and name it doubly linked node. Inside this class, we declare the member variables data. Let's keep it of int type and references to next node and previous node. Then we generate the getter and setter methods for the next node and previous node variables like we did in the node class. And we can use Eclipse to generate these getter and setters for us. Let's write a constructor for this class so that we can create these node objects from integer data. Now let's write another class and name it doubly linked list. And inside this class, we first declare the member variable head of type doubly linked node. Now let's write insert at head method, which takes an int type of parameter, which is the data. Inside this method, we first create a new object of doubly linked node type and name it new node. Then we set the new node's next node as the current head, right? That was the first thing we did in the animation. Then we check if the current head is not equal to null. We set the current head's previous node as the new node. Well, we have to do this null check because if the list is empty, the head will be null. And if we try to access the previous node of a null element, we would get a null pointer exception. Alright. And finally, we make the new node as the head of the linked list. We can also implement the length method inside doubly linked list class, which tells us the number of nodes in the list. But it is same as what you would have already implemented for a regular singly linked list class. So I will just leave it as an exercise here. Similarly, we can override the toString method in the doubly linked node and doubly linked list classes, which are quite easy to follow. Now let's create a new class and name it doubly linked list demo and write a main method inside it. And inside this main method, we create a doubly linked list type object. Let's call it integers. Then we add a few integers to this list. And then we print the list out. Let's run the program. And we can see the order in which the elements are added in the list. You may also want to use the debugger in the IDE to navigate through the linked list to see that all the next nodes and previous nodes are connected properly. You have already seen how insertion sort works and what is the logic behind it. Now, one problem with insertion sort algorithm is that it takes a whole lot of time in moving the data to adjacent slots to make space for the new element that has to be put in the sorted part, right? So if the array is reverse sorted, it just takes a whole lot of time, and that is the worst case scenario for insertion sort. And if the array is nearly sorted, then insertion sort works quite fast, almost taking linear time. Now, instead of arrays, if we store the data to be sorted in a doubly linked list, the time taken to run the insertion sort algorithm improves significantly. Remember, the worst case time complexity still is of the order of n square, but the constant factors are now significantly less. So in reality, the algorithm takes much less time to sort. And the reason is, after we find the place in the sorted part of the array, where the new element from the unsorted part is to be inserted, we don't need to move the elements of the sorted part to make space for the new element. All we need to do is to update the references so that the new element node comes in its proper place. So a whole lot of memory access steps can be saved. Consider this doubly linked list. For running the insertion sort algorithm, we start from the left. So we start from the first element, which is already sorted. Then we go to the next node, which has a value of 2. We use this black pointer to mark the new element from the unsorted part that is to be inserted in the sorted part of the linked list. And we use a green pointer to mark the element before which the new element is to be inserted. And this green pointer keeps moving through the nodes before the current node one by one until we reach a node which has a value smaller than the current node, or if it is null. If you don't remember insertion sort, I suggest that you go back and revise it so that you can understand this part. Now 2 is smaller than 5, and so we move to the previous element. But this is null, and we cannot go beyond this. So our green pointer stops here, and it means that the current node has to be inserted before this null object. So we update the node references in such a way that 2 becomes the new head and 5 becomes the next node to 2, and 2 becomes the previous node to 5. While changing the references, we have to be very careful, because you may miss some reference from changing or updating, which would just mess up the linked list. Alright? So here I want you to be attentive and watch carefully. And just keep in mind that whatever nodes we can access can only be through the black and green pointers. And in our program, we would refer to the black pointer as current, maybe, and the green one as insert after, alright? So we want the current node to be put after the insert after node. To make it easier to follow the process of updating references, we will mark each step on this doubly linked list shown here, which is exactly how our linked list should look like after we are done updating the references. So let's start. First, we can connect the node 5 with node 4. So we have to make the next node of 5 point to 4. But how do we get to node 5? Remember that we have references to the black and green pointers only, and we need to access other nodes using these references. And because node 2 has to be removed from this place and placed elsewhere, which is after the green pointer, we need to connect the previous node of 2 and the next node of 2, isn't it? So we can say black pointers previous node's next node should point to black pointer's next node. By the way, in the program you can name these variables with some more meaningful names. But here I'll keep using black pointer and green pointer so that it's clear which nodes are we talking about. Okay, so we are done updating this reference. Similarly, we can set the previous reference of node 4. So we can say black pointer's next node's previous node is equal to black pointer's previous node. Alright. So we are done updating this reference also. Now as you can see from the final state of the list, we have to make the black pointer's previous node point to the green pointer, right? Because the black pointer node must come after the green pointer node. So let's do that. And we are done updating this reference. Now we are left with these couple of references, after which we will be done inserting this node in the right place. So let's start with this one. We are basically saying that make the next node of the black pointer node point to node 5. But how do we get to node 5? Well, we can use these connections. From the black pointer node's next node, which is node 4, we get to its previous node, which is basically node 5. Alright. So we can say that black pointer's next node is equal to black pointer's next node's previous node. Alright. So we are done with this reference. And now this last one is left out, and this is simple. We just need to do black pointer's next node dot previous node is equal to the black pointer node. Alright. And finally, if the green pointer is pointing to null, it means that the black pointer node should become the new head of the linked list. So don't forget to update that reference. By the way, if the green pointer was not pointing to null, then we don't update the head reference. Alright. I hope you can see that. So after we are done with updating the references, this is how our linked list looks like. Then similarly, 4 will be inserted in the right position. And finally, let's look at one more case when the green pointer does not point to null. Okay. So we have this last element remaining. So the black pointer moves here. And then we try to find which position will this node be inserted. So we start from the previous node, just like we do in the insertion sort. 5 is greater than 3, so we move to its previous node. 4 is greater than 3, so we again move back. And then 2 is less than 3. So the node 3 must be inserted after node 2. Alright. And this time the green pointer is not pointing to null object, which means that the black pointer node will be inserted in a position which cannot be the head element of the list. Let's again keep the final state of the list in front of us, so that it's easier to ensure that we update all the references correctly. And you can use a pen and paper to do the same thing and keep marking the references that you may have updated. And for each update, I suggest that you write it as a statement. And these statements will become your pseudocode. So it will be easier for you to implement. So let's start with this reference. This is similar to the case we saw earlier. And what we are doing is that we are updating the next node of the black pointer's previous node, which is this, to the next node of the black pointer. Alright. And if you recall, we also made the previous pointer of the next node of black pointer point to the previous node of the black pointer. But in this case, we cannot do that because the next node of the black pointer is null. So we cannot access the previous node of a null object. Alright. So make sure that you put a null check while updating the references. So let's mark it as done. Then let's update this reference, which is the previous node of the black pointer. and this must point to the green pointer node. So this one was easy. Now we update the next node of the black pointer node, which must point to the green pointer's next node. Alright. Then we update this reference, which can be accessed as green pointer's next node's previous node, right? And this should point to the black pointer. And finally, this reference is left, which is green pointer's next node, and this should point to the black pointer node, right? So we have updated all the references correctly, and our list will finally look like this. Okay, I want you to implement this in Java or any other language if you are not using Java before you move on to the next lecture. In this section, we will look at two new types of data structures. First, we will see stacks and its implementation using arrays. Then we will move on to the second type of data structure called queues and its implementation using arrays. We will also see what are double-ended queues and how to implement them using arrays. So let's start with the stacks. Stacks are one of the very basic data structures. A stack can be thought of as a container in which we can insert data from the top. So that means that every new data element you push into the stack sits on the top. This operation of inserting new data into the top of the stack is called push. So every new element that you push onto the stack sits on top of the stack. We can also remove or take out data elements from the stack. But note that we can remove only the topmost element of the stack. We cannot take out a data element from the middle or bottom of the stack. So every time we take out an element, it will always be the top element of the stack. We call this as popping an item from the top of the stack, or it's called the pop operation. So what the pop method or operation does is, it removes the top element of the stack and returns it. So if you want to remove the last element of the stack, we will have to take out all the other elements on top of it. There is another operation that we can use on stacks, and that is to peek at the stack. What the peek method does is, it reads the value of the topmost data element without removing it and returns that value. So if we call the peek method on this stack, it will read the value of the topmost element, which is 2. That's it. Stacks are also called LIFO, which stands for last in, first out, because of the way data is arranged in the stack. That is, the last element to go into the stack is on the top, which also happens to be the first one to come out. So to sum up, there are 3 operations that can be carried out on stacks: push, pop, and peek. Now stacks and queues are abstract data types. And what we mean by that is, data structures like arrays or linked lists are real data structures, which are physically represented in memory as such and can hold real data. But stacks and queues are conceptual data structures which are usually implemented using an array or a linked list as the underlying data structure, which can hold the real data that we put in stacks and queues. You will understand it better when we get to the implementation of stacks and queues. So let's see how we can implement stacks using arrays. We know that arrays have a fixed length. So first we declare the maximum size of the array, say 9. And let's declare an array of int type of size 9. Now we have an array of int type and each element is initialized to 0. Now set a reference to keep track of the top of the stack, and we initialize it to -1 because right now there are no elements in the stack. Now let's see we want to insert or push a new element 5. Think about how we can do that. Well, all we need to do is increment the value of top by 1. So it points to the 0th index now. And we update the data at index 0 to 5. That's it. Now let's push 12. So we increment the top by 1 again to make it point to the first index and update the data at index 1 to 12. Similarly, we can keep pushing other elements like this. Now let's see the peek operation. All peek does here is return the element pointed by the top index, which in this case is 2. And the value of top is not changed in case of the peek operation, alright? Let's see the pop operation now. The pop operation, as you know, should remove the topmost element. And how can we do that? Well, it returns the element pointed by the top, which is 2 here, and then decrements the value of top by 1, which essentially is removing the top element because we don't have a reference to that element anymore. And the top now points to the element at index 2, which is 7. Similarly, we can remove the element 7 by returning 7 and then decrementing the value of top by 1. Now, if we remove all the elements of the stack and the value of top is -1 again, we can say that the stack is empty. Let's see the time complexity of these 3 operations we just saw. All the 3 operations that we can perform on a stack, push, pop and peek, are all constant time operations. That is, all of these operations take O1 time. Why? Because the time taken by these operations don't really depend on the number of items that are in the stack. If we want to push a new item, it goes right on top of the stack and we can access that through the top index value, which is immediately available to us. Similarly, if we have to peek or pop elements from a stack, we again access the element using the top index, which does not really depend on the size of the stack. Queues, just like stacks, are also abstract data types. That is, they are implemented using some real concrete data structure like an array or a linked list. As the name suggests, the queue data structure basically is like a bunch of people standing in a queue at a theater to get in. So the first guy stands at the front and then the next guy behind him and so on. So a queue can be thought of as a container whose front end is called the head and the rear end is called the tail. And we can insert and remove data elements from a queue. Let's see how. We insert an element into the queue from the tail end and the element goes forward as much as it can towards the head, like shown here. And this operation is called enqueue. So the enqueue operation inserts a new element from the tail and sort of pushes it towards the head of the queue. We can keep inserting elements like this. Now let's see how we can remove an element from a queue. We remove elements one by one at the head of the queue. That is, the first element at the head is pushed out of the queue first. So here the first element at the head, which is 7, is removed first. This operation of removing an element from the queue is called dequeue, and it always removes the element at the head of the queue. This time, if we use the dequeue operation, the element 12 will be removed. Basically, in queues, elements enter from the tail and leave from the head. If you remember, in stacks, the last element to go in was the first one to come out. But in queues, the first element that goes in is the first element to come out. So queues are also called FIFO type of data structures. First in, first out. Another operation that we can perform on a queue is the peek operation. The peek operation returns the value of the element at the head without removing it. So here the peek operation will return 21. So there are 3 operations that can be performed on a queue, enqueue, dequeue and peak. And of course, we can check the size of the queue or check if the queue is full so that we can use it before enqueuing a new element. We saw the operations we can perform on queues. Now let's try and understand how we can implement a queue using an array. First we create a new array of int type of some size, say 8. And all the elements of this array are initialized to 0. And that's done by Java automatically, so you would know. Since there are no data elements at this point, we can initialize the head and the tail of the queue to -1. Let's say we want to enqueue a new data element 8 in the queue. We can do that incrementing the values of both the head and tail by 1. Because this is the first element in the queue, both the head and the tail should be pointing to the 0th index. Then we update the data at the 0th index of 8, isn't it? After all, if there is only one person standing in a queue, he can be set to be at the head of the queue and as well as at the tail of the queue, right? Now to add another element 12. Remember in the last case, we incremented the values of both the head and tail by 1 because it was the first element. But now we only need to increment the value of tail by 1 for each enqueue operation. So to enqueue 12, we increment the value of tail by 1 and update the data at the first index to 12. After all, the first element remains at the head because that has not moved out of the queue yet. Similarly, we can keep enqueuing elements by incrementing the tail value of 1 and updating the data. Now let's see how to dequeue elements. Now we always remove elements from the head of the queue. So for dequeuing, we need to increment the value of head by 1 so that the head now points to the next element in the queue, which was added right after the one which is being removed from the queue. The dequeue operation will return the value of 8, which is the element at the head, and the head now moves to the first index. As you can see, we don't need to physically remove the element from the array. We just move the head index so that the element is logically removed from the queue. Alright? It's a similar approach that we followed in case of stacks. Alright? So if we dequeue again, it returns 12, which is the element at the head, and the head now moves to the second index. Now tail will remain at its index throughout the dequeue operation. The next operation that we look at is peak. The peak operation here will return 73, which is the element at the head without removing it. As you can see, the dequeue is in a state such that the tail is at the 7th index, which is the maximum index of this array. So now if we want to enqueue a new element, say 27, is it possible to do it? How can we increment the tail? Well, as you can see, we do have some empty spaces in the queue. After all, when some elements have been removed from the queue, we get some space, and hence that space can be reused. So the first thing that we need to find out is if there are any empty slots for the new element to be enqueued. You should pause the video here and think about how you can find that out programmatically. Well, we can find that out by subtracting the head index from the tail index. And if this value is less than the length of the array, which is 8, we can be sure that there is an empty place on the queue. So in this case, the tail is at the 7th index and the head is at the 3rd index. So it is clear that there is in fact empty place in the queue. Now that we are sure that there is an empty place, next we need to figure out where the tail needs to be placed. So we can see that the empty place is at the beginning of the array. So whenever the tail is at the maximum index position and the head is not at the 0th index, we bring the tail back to the 0th index. And then we can update the data at the 0th index to 27. Similarly, we can add another element just like before by incrementing the value of tail by 1 and updating the data at that index. A queue in which we enqueue elements by bringing the tail back to the 0th index after it has reached the maximum index position is called a circular queue, because the tail traverses a queue in a circle to come back to the position it started. We have seen what a queue is and how it functions. Now we will see another type of queue called the double-ended queue or the DQ, which kind of sounds similar to the DQ operation, but it is not that. The DQ data structure is a double-ended queue data structure. Now, before we get into the details of it, I want to tell you that this kind of a queue is generally not used in real-life programming because of its complexity. So we will not be discussing it in depth, neither will I go into its implementation, but we will see an animated overview of its functioning and try to understand the basic idea behind it. A DQ is different from a normal queue in the way that it allows us to add and remove elements from both the head and the tail, unlike a normal queue where we can add elements only to the tail and remove them only from the head. So here we have an empty DQ with its head and tail. So we can insert an element from the right. So when we use the insert right operation, a new element is added to the queue at the tail like shown here. We can also insert an item from the left. So when we use the insert left operation, elements are added at the head of the queue like shown. So basically we can choose to add new elements to either the head or the tail of the queue. Similarly, we can delete elements too, either from the head or the tail. So there would be 4 main operations in a DQ. Insert right or enqueue right, whatever you want to call it. Insert left or enqueue left. Delete right and delete left. Alright. Now let's see how we can implement a DQ using an array. First we create a new array of int type of some size, say 8. Then we initialize the head and tail with a value of -1, since there are no elements in the array right now. Now let's say we want to add a new element 7 from the right. As it is the first element, it doesn't really matter. We do this by incrementing the value of both head and tail by 1 and updating the data at the 0th index to 7. Now when we say we want to insert it from the right, it means that we want to insert it at the tail. Whenever we want to insert a new element at the tail, we need to increment the value of tail by 1 and then update the data at that index. So here, to insert the element 12 at right, we need to increment the value of tail by 1 and then update the data at the tail index, which is the first index right now, to 12. Now let's say we want to add a new element 14 from the left. When we say left, we really mean at the head. But as you can see, we have the head at the 0th index and the tail at the first index. So if we want to insert an element at the head, where does the head move to? As the head can never cross the tail, we cannot move it to the right. So whenever we add an element at the head, we need to decrement the value of head by 1. But since the head is already at the 0th index, we cannot decrement it right now. So what do we do? If you remember, in the case of a circular queue, the tail travels through the queue in a circle. So we can implement the same logic here and make the head move to the last index, which is the 7th index. So now the head moves to the last index and we update the data at that index to 14. Now what happens if we want to add an element, say 9, from the left, that is at the head. Well, to do so, we can decrement the value of head by 1 as discussed earlier. So the head now moves to the 6th index and we update the data at this index to 9. So if we want to add an element from the right, we increment the value of the tail by 1, and if we want to add an element from the left, we decrement the value of head by 1. We can also delete items from a DQ from the head and the tail. Say we want to delete the element from the left, that is the head. The element at the head is 15. So we can do that by simply incrementing the value of head by 1, so that the head now moves from index 5 to index 6, and that's it. As you can see, the head now points to data element 9 and 15 is essentially deleted. What if we want to delete the element from the right? Deleting an item from the right means deleting the element at the tail, which is 13 here. We can delete this item by just decrementing the value of tail by 1, so that the tail now moves to the previous index. As you can see, the tail now points to the element 12, and so 13 can be considered to be deleted. So we can delete elements at both the ends like this. As I said earlier, DQs are normally not used much, so we will not be getting into its implementation details. So we have learnt about simple queues, circular queues, and the DQs. Now there is another type of queue known as the priority queue. But priority queues are very easily implemented with the heap data structure. So we will not talk about this right now, as its implementation and understanding will need some knowledge of heaps. So we will discuss about priority queues in the chapter on heaps. In this chapter, we will learn what recursion is. We will start by implementing the factorial method using recursion. Then we will see how the recursion call stack works. Then we will move on to implementing a couple of more algorithms using recursion, the tar of Hanoi and the merge sort. Alright. So let's start off by revisiting Euclid's algorithm, something which you have already seen earlier. Now this is a recursive algorithm because the GCD method or function calls itself until it evaluates to some integer value which is returned. And the integer value is evaluated when the parameter b passed to the GCD method is 0, and this is called the breaking condition. And it is very important to have a breaking condition in recursive method calls. Until b is 0, the GCD method will keep calling itself over and over. Okay? So recursion is when a method calls itself from within the same method. Now let's look at how we calculate the factorial of a method. So factorial of n is n into n minus 1 into n minus 2 all the way up to 1, right? So we can initialize a variable with a value of 1, and then in a for loop we keep multiplying integers from 1 to n to the result and storing it back in the same variable. And finally when we are done, we return the result, alright? So this way of calculating factorial is an iterative way, because we iterate through all the numbers from 1 to n. But again, the factorial of a number n is defined as this. And it can also be written as n into factorial of n minus 1. We have just grouped the part from n minus 1 onwards, alright? So if we implement factorial recursively, we can write the factorial method like this. Now let's implement the factorial method in Java and run it to see if it works. As you can see, we get a stack overflow exception. So what went wrong? Well, we forgot to put the breaking condition, because of which the factorial kept calling itself over and over unless it ran kind of out of memory. And we will understand why that happens. But the important point is that you must put a breaking condition. Otherwise you will get a runtime error. So we put the breaking condition or the base condition as if n is 0, we return 1. Because factorial of 0 is 1 and factorial of negative numbers is not defined. So if you want to put another check, that is if n is less than 0, we put another exception saying that factorial for that n is undefined. Anyways, so if we run the program again after putting the base condition, we get the correct value of the factorial of this number. So while using recursion in a program, make sure that you always put a correct breaking or base condition. Now, if you compare this recursive program to the iterative one, you can see that the recursive way is much more concise and cleaner. So recursion has its pros and cons. The recursive way makes our problems very concise and easy to understand, but the iterative way performs better in terms of how fast it runs or how much memory is consumed. Also, recursion may cause stack overflow errors in case the depth of recursion is not small. But suppose you have to write a program to solve the Rubik's Cube or to solve the Tower of Hanoi. These kind of programs are very difficult to implement the iterative way. But then recursion requires a little getting used to. So if you are new to this, I advise that you try out all the problems in the chapter exercise and think about simple algorithms which may also be done recursively. Now let's try to understand how recursion works and why would we get that stack overflow error in case you forgot the breaking condition or if the depth of recursion is big. So let's use the factorial program to understand this. Now, as you may know that a program's runtime usually creates a stack, which is called a method stack or a call stack, using which it keeps track of local variables or expression evaluation, etc. Now, this call stack in context of recursive methods is also called as recursion stack. It's one and the same thing, just a different name. Now, let's say that the factorial method is called with a parameter 5. Inside the factorial method, it checks if the parameter is 0 and it is not. So this method returns 5 into factorial of 4. But factorial 4 itself is a method call whose value is not yet known. So this expression 5 into factorial 4 is stored in what is called as a stack frame and pushed into the recursion stack. And now the call is made to factorial 4. So this method is called again with a parameter 4. Then again, call to the factorial method returns 4 into factorial 3, whose value is unknown. So this expression is stored in a stack frame and pushed down the recursion stack. And this keeps on happening until a known value is returned. So now we know that factorial of 0 is 1 and this value is replaced in the stack frame which has factorial 0 as part of the expression to be evaluated. So this value is replaced in that stack frame to get the value of factorial 1 now. And we keep popping stack frames and replacing the calculated factorial values. Until all the stack frames are popped from the recursion stack. And the value of the expression of the last stack frame is the result of the recursive method call. And that is the reason why if you forget the breaking condition, you get stack overflow error, because the method keeps pushing stack frames into the stack, never reaching the breaking condition, and ultimately the stack is full and it overflows. Alright? And sometimes you may also get a stack overflow error even after having a breaking condition. And that would happen if the recursive call is too deep. For example, you call the method with a very large parameter value. That is, there is a whole bunch of stack frames to be pushed into the stack before an answer can be arrived at. In the last section, we saw how a recursion call stack works. Now, can there be a way to avoid stack overflow kind of errors? Think about it. Well, there is another type of recursion called tail recursion, which if optimized for, can avoid stack overflow errors. So the kind of recursion that we just saw was head recursion. So we can write a program using tail recursion like this. We write a factorial method which takes an int type of parameter n for the integer we want to calculate the factorial of, and another int type of parameter result which holds the value of the previous calculation. So every time we calculate the factorial, the result of the calculation is passed in the result parameter. You will see what I mean by that in a second. Then we write the breaking condition, where if n is equal to 0, we just return the result itself, because that should be holding the value of the factorial. Otherwise, we recursively call the factorial method, and every time we do so, we decrease the value of n by 1 and pass the result as result into n, so that we keep moving towards the breaking condition. We usually overload the method to make its use easier. For example, if we expose this raw method, many programmers might make a mistake initializing the value of result, or they have to know the internal details of the method. We would rather like them to just call factorial and pass the appropriate number, which in turn may call the other method. Note that this result parameter is called accumulator because it accumulates the value of previous calculations, giving us a definite value every time. Now, if you notice, using this type of recursion does not need stacks because we have a definite value throughout the method call, right? After all, the stack frames are used to keep track of intermediate calculations. But here in tail calls, we are passing a definite value each time. But the compiler of the language should be able to identify this as tail recursion. And unfortunately, Java is not able to do so. So even if you write this kind of code in Java, it will still make use of recursion stack and stack frames and is not able to take advantage of tail recursion. But some functional programming languages like Haskell, ML, etc. are able to optimize for tail recursion. Hence it becomes quite useful there. To show the application of recursion, there is nothing better than the puzzle Tower of Hanoi. Tower of Hanoi is a very interesting puzzle, and many of you may already know about it. So there is a story that there's a place called Hanoi, I think in Vietnam, where there are 3 towers and with about 100 disks, and the monks there have to move all the disks from one tower to another tower by using certain rules. And it is said that by the time all the disks are moved from one tower to the other, the world will end. But the world has already ended many times now, and it's probably become quite boring to even talk about it. But anyways, so let's go over the rules of the puzzle. Okay. Now here we have 3 towers A, B and C, and we have some disks in tower A, which are arranged in the increasing order of size from top to bottom. And what we are supposed to do is to move all the disks from tower A to tower C using tower B as an intermediate, such that at no point of time a bigger disk comes on top of a smaller one, alright? And one more rule is that we can only move one disk at a time, alright? So let's look at a few examples to make the idea clear. So let's say we just have one disk. So this is simple. We can just move disk 1 from the tower A to tower C directly and we are done. By the way, we have named the towers and numbered the disks so that we can track the movement. And in our program, when we write one, we will be printing out these messages. Alright. So if there are 2 disks, we number them as 1 and 2, 1 being on top of 2. Alright. And this order of numbering the disk is important for our algorithm. So in general, we'll start numbering the topmost disk as 1, which would also happen to be the disk with the smallest radius, and then keep increasing the numbers as we go down the stack of disks. And this case of 2 disks is also quite simple. We first move disk 1 from tower A to B. Then what do? Move disk 2 from tower A to C, right? and finally move disk 1 from tower B to C. Alright? And this was also quite simple and something which everyone can figure out. Then what about if we have 3 disks? And you will notice that by adding more disks, the complexity of the problem increases, and slowly with few more disks, it will become much harder to write all the steps correctly. Anyways, so before moving on, you may want to pause the video here and write the steps yourself. This one is also quite easy. So what we can do is that we move disk 1 to tower C from tower A, then move disk 2 from A to B, move disk 1 from C to B, move disk 3 from A to C, and now we would like to move both these disks 1 and 2 to tower C. But because we can only move one disk at a time and without keeping the bigger disk on top of the smaller one at any point of time, we first need to move disk 1 from tower B to tower A, and then move disk 2 from tower B to C, and then finally move disk 1 from A to C. Alright? And this was a little more intense than the first two cases. And as the number of disks increase, identifying the steps become increasingly complex. And actually it is so complex that it will really be hard to write a program which moves these disks iteratively. And this is where recursion comes to help and makes this problem quite easy to program. All you have to do is to focus a little and align your thoughts along the lines of recursion. So let's say we write a method move which takes 4 parameters. The first one is the number of disks that need to be moved. And then the other 3 parameters can be of char or string types representing the towers. So the first one out of these 3 is tower from. So we passed A here. The second is tower 2. That is, the disks are to be moved from tower A to tower C. And the third parameter is the intermediate tower, where we pass B as argument. So when we call the move method with these parameters, we mean that move n disks from tower A to tower C using tower B as the intermediate. And first you should convince yourself that this is possible. That is, we can move all these disks from A to C using another tower. And if you are convinced, let's proceed. So if we can do that, it essentially means that we should be able to move these n-1 disks from tower A to tower B using C as an intermediate, right? Think about it. Because the nth disk is the largest in radius, it can remain untouched when we are moving those other n-1 disks like that, right? So we should be able to move these n-1 disks from A to B using C, which means that we can call the move method for n-1 disks from A to B using C, isn't it? Notice that the order of arguments for from tower to tower and using tower has changed, alright? Then we can move disk n from A to C, which is what we can print. And then we recursively move these n-1 disks from tower B to tower C using tower A. So we can again call the move method recursively with this different set of parameters. And this whole recursive approach just needs to be synced in a little. And to help with that, let's revisit that 3-disk example again. So here what we are saying is that we want to move 3 disks from tower A to C using tower B, which means that we can move 2 disks from tower A to B using C. And what we did earlier was that we first moved disk 1 from A to C, then we moved disk 2 from A to B, and then moved disk 1 from C to B. So essentially the state of the system right now is exactly as if we moved the 2 disks from tower A to B using tower C, right? Which was done recursively. And we don't really care about the details. So we are done with this part. Now we move disk 3 from A to C. And finally, we move these two disks from B to C using tower A. And if we see the details, that is what we end up doing, right? So as you can see, thinking recursively makes this problem much easier to solve, but of course it needs a little practice and patience to be able to align your mind in that direction. And of course, we need to put a breaking condition. But let's implement this program and we will talk about the breaking condition there. Before moving on to the next lecture, I suggest that you try implementing the program yourself first. It's okay to try and fail, but it's not okay not to have tried. Alright? Before explaining the implementation, let me run the program to show you what exactly needs to be done, just in case you're not aware of this problem. So we are supposed to implement this move method such that it takes these parameters which was already discussed earlier. And we call this move method from the main method. Like here we say move two disks from tower A to tower C using tower B, alright? And when we run this program, we get the exact sequence of steps that are supposed to be executed to complete this task. So as you can see, we first move disk 1 from A to B, then move disk 2 from A to C, and finally move disk 1 from B to C. Similarly, let's try to print the steps for 3 disks. So if you have understood the problem, pause the video here and implement it before moving on. So let's start implementing the move method. As you can see, we just have these 3 lines of code here, which we have already seen earlier in the animation. So what we are essentially doing is that we are just picking up the first n-1 disks and moving them from tower from to the intermediate tower using the to tower. Then we move the only disk, which is the nth disk, from tower from to tower 2. And then we recursively move that bunch of n-1 disks from the intermediate tower to the to tower or the destination tower using the from tower as an intermediate. Alright? Just close your eyes and visualize what's happening. It's quite straightforward. Let's try to run the program after writing the main method and calling the move method from the main method. And as you can see, we get a stack overflow error because we didn't put the breaking or the terminating condition for this recursive call. And what would be the breaking condition? Think about it. Well, the breaking condition is when we only have one disk to be moved, right? And in that case, what do we print? Well, we simply move disk 1 from the from tower to the destination tower, and that's it, right? That is the case we started with when we were showing the animation in the previous video, right? When we only had one disk to be moved from tower A to tower C. And now if you run the program, everything works fine. So if you look at the code, it's quite easy to implement the Tower of Hanoi puzzle using recursion. You just need to get used to it, alright? Now we will learn another sorting algorithm called merge sort. This algorithm is a recursive algorithm and works very well for large sets of data. The most important step in the merge sort algorithm is the merge step. In this step, we take two individually sorted arrays, alright, and merge these two such that the resulting array is also sorted. So if the two arrays that we start with are in ascending order, the resulting array, which would contain all the elements of the two arrays, should also be sorted, okay? And how do we do that? Let's understand with the help of an example. We have these two arrays which are individually sorted, right? Elements 2 and 9 are in ascending order in the left array, while elements 7, 8 and 12 in the right array are also sorted. And if we merge them into one single array, so let's say we have a resulting array of size 5, which is equal to the sum of the individual lengths of the two arrays. And the way to merge these two arrays is that we start by comparing the first elements of both the arrays, alright? And whichever element is smaller, we put that in the resulting array. So out of 2 and 7, 2 is smaller. So we place 2 in the resulting array and move our pointer to the next element of the left array, because we copied the element from the left array, okay? Then we compare 9 and 7. And now 7 is smaller out of the 2. So we copy 7 to the resulting array and move the pointer to the next element of the right array. Then we compare 9 and 8, and 8 being smaller, we copy to the resulting array and move the pointer. Then we compare 9 and 12, and because 9 is smaller than 12, we copy 9, and now we are at the end of the first array. So we just copy all the remaining elements of the right array over to the resulting array. And this is how we can merge two individually sorted arrays into a complete sorted array. But this was only the merge step. There are more details for the merge sort algorithm. Let's say we are given an unsorted array of integers. As said earlier, merge sort is a recursive algorithm. So we are calling merge sort method on this array. And what we really do is that we break down this array in two logical parts about midway, and then call merge sort on these two arrays, alright? That is, we try to sort these individual arrays. The idea is that we will sort these two arrays using merge sort and then merge these two arrays into one single sorted array, alright? So we again call the merge sort algorithm recursively, further breaking down these two arrays into two parts each, and then call merge sort on these smaller arrays. And we keep doing that until we have broken the array into small arrays of one element each. Alright? Now, because they are arrays of single elements, individually they are already sorted, isn't it? So now we can start merging them together. So we merge the first two arrays into a single array so that the resulting array is sorted. And similarly, we merge the other arrays as well. So now we have these four arrays which are individually sorted. So we can merge them together into two arrays, which will themselves be sorted. And finally, we merge the two arrays into a single sorted array, alright? Just think about it for some time, it's not very difficult. Now let's look at the pseudocode for merge sort. So here we denote the array as capital A, and what we are doing here is that we are saying merge sort array A from start to end. And what is start and end? Well, they are indexes of the array representing the part of the array we want to merge sort, alright? So basically we don't really physically break down the array into smaller parts, rather we do a logical breakdown, and start and end indices help us keep tab on which part of the array is being merge sorted. And just to make it clear, merge sort will be called on array A with the start index as 0 and the end index as 7, because the length of the array A is 7, alright? Of course, start is less than end. So we go inside the block of code and calculate the middle, which will be 3. Then we call merge sort recursively on array A, but only on the first part of the array from index 0 to 3, alright? Now the next statement will not be executed right away, because the call will again go to the merge sort method with these arguments. The next statement will only be executed when the merge sort method returns, which will happen once it reaches the breaking condition, right? So now merge sort is called from 0th index to the 3rd index. Again, start is less than end. So middle is calculated to be 1. And then we call merge sort with 0 as a start and 1 as end, which means that this time we are merge sorting the first two elements. Merge sort called recursively again, middle is 0, and merge sort again called, but this time with 0 and 0 as arguments. That is, we just want to merge sort the first element. So now when merge sort is called with these arguments, the method would return because there is only one element to be sorted now. And one element array is already sorted, so we don't do anything. And because this method returns, the next statement calling merge sort will be executed on array A with arguments start and end as 1 each. That is, we want to merge sort this element of the array. And here too start is equal to end, hence the merge sort method will return without doing anything. So now we will call the merge method, which will merge these elements of array A, right? Because we just said that this can be logically seen as two single element arrays, and we are merging these two now. We will come to the merge routine, but for now just understand what is merge sort doing. So after the merge method returns, the data in the array A will look like this. 23 and 5 should have exchanged places. And now we will come to the stack frame where a call to merge sort A03 was made. And now merge sort A01 has returned after merging the first two elements. Now call to merge sort A23 is made, which means that this part of the array will be sorted now, alright? So merge sort will be called recursively just like we saw in the previous example. And when it returns, the merge method with 0, 1 and 3 as parameters will be called, which will merge these two individually sorted parts of the array. So that after this merge call returns, the array will look like this. This was quite intense. I hope you have understood what's going on. Or you can try putting the call stack by writing the sequence of calls on a piece of paper. And now we will get to the merge routine. Let's get to the pseudocode of the merge method. This is quite simple. Just keep in mind that we have divided the arrays logically. One part of the array is from start to mid index, while the other part of the array is from mid plus 1 index to the end index, alright? So let's say we are in this last step of merge, when these two parts of the array have been recursively sorted by merge sort. And now we are doing the final merge step. While merging, if we overwrite on the array, we will lose the data, right? So the first thing we can do to keep things simple is we create two temporary arrays and copy the elements from this main array over to those two. So let's first find the size of the arrays. For the left array, the size may be found as mid minus start plus 1. And for the second array, the size will be end minus mid. And you can see both parts contain 4 elements each, so that should be the size of the two arrays. So let's create two arrays of sizes n1 and n2 respectively and name them left and right. Then we copy the left part of the main array into the left array and the right part of the main array into the right array. And the pseudocode for these two steps is very simple and straightforward. In these two parts, we are just doing that, copying data from the main array over to the left and right arrays. Now we need to start going through all the elements of the left and right array. So let's declare two variables I and j and initialize them to 0. These will act as indexes or pointers for the left and right arrays respectively. By the way, the I and j variables that we used in the for loops are different, alright? They are local to the for loop and their scope ends as soon as the for loop exits. Then we write another loop to go over the indices of the main array, because now we will be merging the left and right arrays into the main array A. alright? And to do that, we first compare the elements at ith index of the left array and jth index of the right array. If the ith element in the left array is smaller, we assign it to the kth element of the main array and then increment I, that is, go to the next element of the left array. Otherwise, we assign the jth element of the right array to the kth element of the main array and increment the value of j. And we can keep doing this for all the indices of the main array, alright? So in this example, we first compare 2 and 7, and 2 is smaller, so we copy it over to the kth element of the main array and increment the value of I. Because k is used in a for loop, its value will also be increased by 1 in each iteration. So now k moves to the first index. Then we again compare ith element of the left and jth element of right. And 5 is smaller than 7. Hence we assign it to the kth index of a, alright? And we increment the value of I. Now we compare 8 and 7. And 7 is smaller. Hence we place 7 at the kth index of a. And now we increment j to move to the next index. And we keep doing this until we reach the end of the arrays. So now both the left and right arrays are merged into the array A such that A is completely sorted now. By the way, here we have shown the pseudocode. When you write the real Java code, make sure that you check for boundary values of I and j while accessing elements from the left and right arrays. Otherwise, you may get array out of bound exception, alright? I will attach the Java implementation for it right here in this lecture, but make sure that you try to implement it before looking at the solution. Now let's see how much time does the merge sort algorithm takes. That is it good or bad compared to the other sorting algorithms which we learned earlier, like insertion sort. So how do we get an estimate of time? In this algorithm, the array is logically broken down into smaller parts, right? So let's say that this is the height or depth of recursion. And we can say that each of this breaking step creates a layer, kind of, okay? So we will generate h layers from the full recursion, alright? Now in each of the horizontal layers, how many comparisons are made? Well, there are n elements in the array, hence we will end up making n comparisons. And with all the copying of elements etc. in each layer, the number of operations will be proportional to n, isn't it? And because there are h layers, hence the total number of operations must be some function of h times n, right? So all we need to do now is to find the height or depth of recursion. So let's do that now. Let's see how many logical arrays do we have in each layer. In layer 1, how many arrays do you see? 1, right? Because this is the start of recursion and we have not really broken down the array at this point. Then in level 2, we have 2 arrays, which is 2 raised to the power of 1. Then level 3 has 4 arrays, or 2 raised to the power of 2. And how many arrays will the last layer or layer h have? It should have 2 raised to the power of h minus 1 arrays, isn't it? That is, if we just follow the power of 2 pattern. And how many elements are there in the array? Well, in general, we have n elements, right? So this number of arrays should be equal to n, because we keep breaking down to a point where we have single element arrays. So we can say that 2 raised to the power of h minus 1 should be equal to n, or h is equal to 1 plus log base 2 of n. So the time complexity is n times h, or it is of the order of n log base 2 of n. So merge sort is a really fast algorithm if we look at the time complexity. But in reality, it is not great for a small number of items because the constant factors are too large. But yes, if you want to sort larger sets of data, this algorithm is to be used. And actually, the Java collections framework uses merge sort as its default sorting algorithm. In this chapter, we will learn binary trees, and more specifically binary search trees. Binary search tree is a very versatile data structure. That is, it is really fast to insert items into it. It's fast to delete items from it, and it's pretty fast to search items in a binary search tree. If you compare sorted arrays and linked list data structures, we see that search is fast in a sorted array, but quite slow in a linked list. Inserting an item is slow in a sorted array, while it is very fast in case of a linked list, that is, if we insert the item at the head. Alright? Then deleting an item is also slow if we used a sorted array to sort items, while it is fast if we used a linked list. Binary search trees are very balanced in the sense that all these common operations like insert, delete and search take about the same time, which is of the order of log n, alright? And we will see how to arrive at that slightly later in the chapter. So let's see what a tree data structure is and know about some commonly used items related to it. A tree data structure may be visualized to be something like this, where we have the nodes which contain the data, and the nodes are connected to other nodes through what are called as the edges. And it's just like we connected the nodes of a linked list through object references, okay? The node at the top of the tree is called the root node. And in a tree data structure, there can only be one root node. So just as the linked list data structure had a reference to the head node, a tree data structure has a reference to the root node. And all the other nodes can be accessed through that. There is one more property of the tree data structure, and that is to search any node of the tree, there must be only one path from the root node. Alright? For example, if these two nodes are connected, then to search the F node, we can start from the root node A, go to C and then F, or we start from A, then go to C, then G and then F. So there are multiple paths from the root node to reach the F node. So that is not allowed in a tree data structure. Alright? Any node other than the root has exactly one edge running upwards to another node. The node above is called the parent of the node. For example, the F node has exactly one edge running upwards to the C node. So the C node is said to be the parent of F. Actually, C is the parent of both F and G nodes. So F and G nodes are called the children of the C node. Then a node which has no children is called a leaf node. Any node may be considered to be the root of a subtree, which consists of its children and its children's children and so on. The level of a node tells us how far it is from the root. For example, the root element is assumed to be at level 0. Children of root are said to be at level 1. Then their children in turn are said to be at level 2 and so on. Now that we know what a general tree data structure is, let's look at what a binary tree is. A binary tree is one in which every node can have at most 2 children. That is, a node may have no children, which makes them a leaf node, or a node may have only one child, or it may have 2 children. But none of the nodes can have more than that. That's why they are called binary trees, because binary means 2. Now, how do we represent a node in a binary tree? Well, a node contains some data, just like we held data in the node of a linked list, and it also have references to its left and right child, which are themselves tree node type of references. Alright? So we can call them left and right, or left child and right child. And of course, the child reference may point to some tree node type of an object. Let's implement some code in Java. In the IDE, let's first create a package for this chapter. and then create a class named TreeNode. Let it contain integer type of data, or if you are aware of generics in Java, you can parameterize this data. But here I'll focus more on the data structure and algorithm part. Then we can write other two member variables representing the left child and right child, both being of type TreeNode itself. Let's write the getter and setter methods for left child and right child. And only the getter for the data. Because once we set the data in the node, there is no need to change it. And we will be setting the data through the constructor. As a good programming practice, immutable objects are good things. So here the node object is not completely immutable because we may need to change references to left and right child. But we should at least keep the data from changing once it has been set in a node. So we don't provide a setter method for the data member. Now we can write a constructor which takes the integer data as parameter so that we can easily create node objects from this data. Now we create another class representing the binary tree object. As said earlier, the binary tree itself contains the reference only to the root node. So let's create a member variable named root, which is of type TreeNode, right? And then we can write methods like insert an integer object in this tree, or find an integer object in this tree. And here we have returned the tree node because we just want to return the node containing the integer data, alright? Or we can delete an integer from this tree object. And that's it. We have pretty much implemented a binary tree, and of course we need to implement these methods that we wrote. So let's do that in the next lecture. As said earlier, the node in a tree contains the data. For example, the tree shown here contains integer data, but it may also have other kinds of data like user data or any other types of object. But let's keep it to integers in our discussion. Now, if the data is randomly placed within the nodes of the tree, it is not very useful, alright? At least for searching data or inserting data, etc., which are the typical operations we do with the tree data structure. So mostly we don't really use a binary tree data structure as such. Rather, we use another variation of it, which is called as binary search tree, alright? So what is binary search tree? Well, a binary search tree is a binary tree with a special property that for any node, all the children to the left, which means its immediate left child and then the grandchildren and so on, have a data value less than that of the parent node itself, alright? So let's consider the root element. All its children on the left have data values less than the root, alright? And all the children to the right of the node have data value greater than that of the node. And this is true for every node. That is, if you pick any node, this property will be true. Let's take another example. If you consider this node, which has a value 33, all descendants to the left have values less than 33, while on the right side, all nodes have a value greater than 33. And keeping this property in a binary tree makes it quite fast to search items, alright? So just keep in mind, left child and its children have values less than the parent, while right child and its children have values more than the parent node. And this is what a binary search tree is. Let's look at how to search for an item in a binary search tree. So let's say this is how the data is laid out in our binary tree data structure. And we would like to find the integer 52 in this tree. And remember, we always start from the root, because as you already saw earlier, the tree has a reference to the root node only, okay? And if we find the data in the tree, we will just return the node object itself. Otherwise, we'll return a null. So how can we do this? Well, we start at the root of the tree and compare the data in this node to the data we are searching for. And if it is equal, we just return the root node. So in this case, as you can see, 52 is the root node, so we just return that. Now let's say we would like to find 39 in this tree. So again, we start at the root and compare it to the data we are searching for. Here 52 is greater than 39. So we can be sure that the node 39, if it exists in the tree, will be on the left side of the root node, because all children smaller than this node will have values less than 52. So now we move to the left child of the root node, which is 33, and compare that value with 39. Since 33 is smaller than 39, we can be sure that if the data exists in the tree, it will be on the right side of this current node. Suppose this node would have been greater than 39, we would have to go to the left side of this node. Anyway, so now we move to the right child of the node 33, and as you can see, the value of the current node is equal to 39. Hence we found the integer value and return the current node. Alright. So when searching for an item in a binary search tree, we start at the root, compare the item to be searched with the root. If it's equal, we return it. If not, we check if it is larger or smaller. If it is smaller, we search the left subtree, and we do that recursively, because as you will see in the code, it is much easier to do a recursive search than an iterative one. Alright. And if it is larger, we search the right subtree recursively. Now it is quite easy to implement search or find if we do it recursively. Alright. But let's first go to our binary tree class and rename it to binary search tree, because as explained earlier, we are dealing with the binary search tree data structure. So let us select the class name by double clicking on it, then right click, go to the refactor menu item and select rename. And now let's rename it to binary search tree. Alright. So let's implement the find method inside the tree node class. Alright. And we do this because we want to find an item recursively. And if you don't understand it, just hold on a little and let's implement it, and you should be able to understand what we are doing. So we write the find method, and the first thing to do is to check if the data contained in this node object is equal to the integer data we are looking for. And if it is equal, we just return this node object, right? Now, if the integer data we are looking for is less than the current node's data, then where should we look? We should check the left child, right? Because there's no chance of finding it on the right side. And here we do a recursive search. So we just call the find method on the left child, okay? And return the result. But the left child of a node may be empty, in which case we should not call the method find. Rather, the search would have ended returning a null. That is, no node was found containing that integer data. Also, if the left child is null and we try to invoke some method on it, we will get a null pointer exception. So we need to put this additional check that we try to find an item from the left child recursively when the left child is not equal to null. Otherwise, we need to go to the right child. Again, only if the right child is not equal to null. So we say if right child is not equal to null, we return right child.find data. And if none of these cases work, we just return a null, which means that no tree node was found to contain that data. Alright. And now we can go back to our binary search tree class. And in the find method, we can say if the root is not null, we can return root.find data, because the search will be done recursively. Otherwise, we just return a null. Alright. And this is not very difficult. Just think about it a little and get used to it. We saw how to search for an item in a binary search tree. Now let's see how to insert a new data item in it. When inserting a new node, we essentially keep looking for a place where to insert this new node such that the binary search tree property is not violated. That is, the right child should be greater than or equal to the current node and the left child should be less than the current node. And well, we can do the equality thing for the right child in case duplicate values are allowed. So if the data is equal to the current node, we insert the new value as a right child. But that may not be the immediate right child, alright? We do the insertion recursively. Let's see what I mean. Let's say we have to insert 63 in the binary search tree shown here. We start at the root and compare the two values. So in this case, 63 is greater than 52. So we know that it must be inserted somewhere in the right subtree. So we move to the right child of this root node. Again, we compare the two values. Since 63 is smaller than 65, we know that it must be inserted somewhere in the left subtree from this node. So we move to the left and now compare these two values. Now 63 is greater than 60, right? So we will need to insert it somewhere in the right subtree. But this node does not have a right child, which means that 63 must be inserted as the right child of this node, isn't it? And this becomes the breaking condition for recursion. Think about it. Let's implement the insert method now. Let's go to the tree node class and write the insert method. And what we can do is that we check if the integer data to be inserted is greater than or equal to the current node's data. We do something which we'll come back to in a moment. Otherwise, we do something else, which is inserting the node somewhere in the left subtree. So if the data to be inserted is greater than or equal to the current node's data, what do? We said that if it does not have a right child, this data to be inserted will become the right child of the current node, isn't it? So let's do that. Otherwise, we can recursively insert the data into the right child node, alright? So again, you can see that recursion makes things quite simple. At least we don't need to write lengthy code. It's quite crisp and elegant code. And we do a similar thing for the other case. But instead of the right child, we check for the left child, alright? And then in the binary search tree class, we write the insert method and check if the root is null, then the current data should become the root, right? Otherwise, we call the insert on the root so that the data is inserted at the right place using the recursive method that we just wrote. Let's see another operation on binary search trees. How to delete a node. The delete operation is quite complicated compared to the commonly used operations performed on a binary search tree. The first step in deleting the node, as you can guess, is to find the node to be deleted. After that, there are three cases to be considered. The first one is that the node to be deleted is a leaf, that is, it has no children. Then the second case is when the node to be deleted has one child. And the third case is that when the node to be deleted has two children. And we have to deal with these cases because we need to rearrange the children of the deleted node so that the binary search tree property is maintained. The first case is when the node to be deleted is a leaf. So say we have to delete the node 34. First we search the node containing 34, right? So we start at the root and search for the node like we saw earlier. After finding the node, we check if it is a leaf. And here in this example, node 34 is a leaf. That is, this node does not have any children. But how do we delete it? Well, it is very simple. As you can see, the node 34 is the left child of the parent node 39. all we need to do to delete the node 34 is set the left child of the parent node 39 to null. That's it. The node 34 will automatically be deleted because of Java garbage collection. But you have to be very careful. Note that when you search for the node to be deleted, we must make sure that we have a reference to the parent node also. Alright? Because from the node to be deleted, there is no way that you can go to the parent node, which means that you will also not be able to access the left or right child member of the parent. So it will not be possible to change the necessary references for deletion. And we also said that this node will be automatically deleted because of Java's automatic garbage collection. When Java sees that there is an object which does not have any references to it, it treats that object as garbage and removes it, thus freeing the memory. So let's first implement this first case before moving on to the second one. Let's write the delete method in the binary search tree class. And here we are going to use an iterative approach instead of a recursive one, because we also need to keep track of the parent. So what we need to do is that we need to track the node to be deleted, its parent node, and whether the node is the left or the right child of the parent. Okay. So let's create these three variables: current, parent, and is left child. And we initialize the current and parent to the root object, and initialize is left child to false or true, whatever you want, because it will get updated to the correct value as our program runs. But we need to start somewhere. Anyways, now the first thing we do is to check if the current node is equal to null, because that will happen when the root is null, which means an empty tree. So we don't do anything and just return immediately. Otherwise, in a loop, we check if the current node is not equal to null and its value is not equal to the data value of the node to be deleted. And we should do the null check here, because once the current reaches null, it means that we have reached the end of the tree. So the loop must exit. Remember, right now we are trying to identify the node to be deleted, which will be represented by current, and the parent of the current node. So as long as the data does not match, we set the parent to the current node, alright? And then move the current node to one of the current node's right or left child, depending on whether the data passed is larger or smaller than the current node's data value. And we also set the is left child variable to keep track of which way the current node went. So after this loop is over, we will have the current point to either the node to be deleted or null, right? So again, if it is null, we don't need to move ahead and return from here, because that means this data is not found in the tree. Otherwise, we have to delete the current node, keeping the binary search tree property intact. So now we come to implementing the case 1 where the current node does not have any children. That is, it is a leaf node. So we check if it does not have any children. Then we go in and check if the current node is pointing to the root node. That is, the root itself contains that data. And if this is the case, we need to delete the root. And because the root doesn't have any children in this case, we just set the root to null. Otherwise, if the current node is any other node, then we check if the current node is the left child of the parent or the right child of the parent by using the isLeftChild property. And we set the appropriate child of the parent to null. Alright? And this case 1 is the simplest of all. Now in the second case, the node to be deleted has one child. For example, let's say we have to delete the node 72. The second case is also not very difficult to handle. So assuming that we have found node 72 as current and its parent, which is node 78. But now as you can see that this node 72 has a left child 70. So if we set the left child of the parent to null, node 70 will also be lost because it will lose contact from the tree. All we want to do is to delete the node with value 72. What we need to do is to point the left child of the parent, point to the child of the current node to be deleted. That is, now the left child of node 78 will become node 70, and thus node 72 will be ready for garbage collection. Now what if that single child of node to be deleted itself has children? Well, as you can see, it doesn't really matter because all we are doing is connecting the child of the node to be deleted to the parent of the node to be deleted. So even if there is a subtree underneath it, it will automatically become a part of the whole tree. So we don't have to do anything special for that. Now let's implement this second case in Java. We continue our line by this other condition. If the node to be deleted, which is current, has only left child, that is the right child is null, if current is equal to root, what should happen? The root of the tree should now be the left child of the current, isn't it? Because now the root is being deleted and there is no right child of the root or current. Else if current is the left child of the parent, then the left child of the parent should be assigned the left child of the current node, right? Because we are dealing with a single child case and current does not have a right child. Then if the current node is not the left child of the parent, that is, it is the right child, we set the right child of the parent to the left child of the current, alright? I advise that you draw these cases with a pen and paper to get clarity on what is happening. It's really quite straightforward. Similarly, if the current body only has a right child, we do a similar thing. So let's just copy these statements from here and paste it in this block and make appropriate changes. So now current only has a right child. So in this case, we can set the root to current.getRightChild. Then here too, in these statements, instead of current's left child, we need to use its right child. Alright? So we are done with case 2 now. We saw the first two cases that we have to consider while deleting a node from a binary search tree. Now let's look at the third case. In the third case, the node to be deleted has two children. And this case is the most complicated of all. Let's say we have to delete the node having data 33. Now this node 33 has two children, 25 and 39. So how do we delete this node? Think about the options. Can we replace the node 33 with this node 39? Well, if we do that, you can see that node 39 will have three children and that is not a binary tree, right? So we cannot do that. Well, we may try to connect these two nodes, the parent and the right child of the node to be deleted. But if we do that, you can see that this whole subtree will be lost. So we can't do that either. Now think about this. What we really want to do here is find a replacement for the node 33 from within the tree such that none of the nodes are lost and the structure of the binary search tree is also maintained. So which node should come here? Well, that should be the node having data that is just greater than the data in the node to be deleted. Or we want a node whose data should be greater than the current node but less than the right child of the current node. So after going to the right child of current node, we keep going to the left child until there is no left child, right? And why do we do that? Well, all nodes in the right subtree has numbers larger than the current node. But if we keep going to the left in the right subtree, we will be going to smaller and smaller numbers, which are still larger than the current node. And this node is called the successor of the current node. So we would like to bring the successor to the place of the current node. And to do that, the left child of the current node should become the left child of the successor, right? Then the right child of the current node should become the right child of the successor node. then we need to break the connection between the parent of the successor node and the successor. And finally, the left or right child of the parent node should now be the successor node. So if we change these connections, our tree should look like this, which is perfect. Now, what happens if the successor node has a right child? Well, before that, can the successor node have a left child? Well, no, it cannot, because then that would become the successor. But it may have a right child. And in that case, when we want to bring the successor to the place of the node to be deleted, then the right child of the successor should now become the left child of the parent of the successor. Alright? Rest of the connections need to be set just as what we saw earlier. So after doing that, this is how the binary search tree looks like. Now I'll not implement this part in the video lecture here and add it as an attachment, but in the next section I'll show you a trick that is quite common to soft delete the nodes instead of actually deleting them because of the complications involved in the delete method. As you saw, the delete operation is very complicated, and to avoid this in practical use, we use something called as soft delete. And what we do is, when a node is to be deleted, it is marked as deleted without actually deleting it. But then whenever we traverse the tree or search for an item, we need to make sure that we don't consider those nodes which are marked as deleted. Alright? So for that, we first create another field inside the tree node class. Let's name it isDeleted and initialize it to false. Then let's write a method called delete on this tree node. And all this does is that it sets the value of isDeleted to true. And let's write another public method to read the value of isDeleted field. Alright. Then let's go to the binary search tree class and comment out this delete method. Let's rewrite the delete method. And here, all we need to do is to find the node with this data and just mark it as deleted. That's it. And in the find method of the tree node class, we can just make this change that it returns this node if the data is equal and this node is not marked as deleted. Alright. This approach works quite well, especially if you are not dealing with a whole bunch of deletes. Alright. Now let's find the smallest and largest data values contained in a binary search tree. So if you look at this example, can you find which node contains the smallest value and which one the largest? Let's find the smallest one first. All we need to do is to use the binary search tree property. That is, for any given node, all values contained in the left subtree are smaller, and those in the right subtree are larger than the value in that node. So to find the smallest value, all we need to do is start from the root and keep going to the left child until we reach a node which does not have a left child. Alright? And that node should contain the smallest data value. So in this example, the smallest integer is 12. And we can find the largest integer in the same way. Keep going to the right child until we come to a node which does not have a right child, although it may have a left child. Alright. So this node contains the largest value in the binary search tree. And you can do it iteratively or recursively. I will show you the recursive solution and leave the iterative solution as an exercise for you. So let's go to the tree node class and add a new method called smallest, which returns an integer, because we are assuming that our tree contains integer data. In case you were using generics, you could have used the generic type parameter as return type here. Anyways, so this method will return the smallest integer value contained in the subtree, whose root is the current node. So here we say that if the current node's left child is null, alright, we return the data contained in this node. Isn't it? Otherwise, we recursively call this method on the left child of this node. That's it. Similarly, you can add the largest method in the tree node class. Now let's go to the binary search tree class and add the largest and smallest methods in it. And here we call the smallest and largest methods on the root of the tree. Alright. One of the things that we want to do in case of a binary tree data structure is to go through all the nodes of a tree, maybe to print the node values or do some operations. The point is, we need to be able to go through all the nodes inside a binary tree. The three most common ways to traverse a binary tree are these: in order, pre-order, and post-order. In-order traversal is probably one of the easiest and most commonly used way of traversing a binary tree. Pre-order and post-order traversals are usually required for compiler kind of programs where the program has to go through the abstract syntax tree or evaluate expressions, etc. We will not get into these kind of details in this course though. So let's start with in-order traversal. In case of in-order traversal, we first traverse the left subtree, and this is done recursively. So first we traverse the left subtree, then we go to the root of the tree, and finally we traverse the right subtree recursively. So if we had only these three nodes in the tree as shown, first we go to the left child of the root, that is 33. Then we go to the root, 52. And finally we go to its right child, 65. But what about a more complicated case? In this example, for in-order traversal, we first traverse the left subtree. Then we visit the root node, and then we traverse the right subtree. But when we say that we traverse the left subtree, it essentially means that we follow the in-order traversal within this subtree also. Which means that within this subtree we traverse this subtree, which means that we first traverse this subtree, but this is a single node, so let's print 12. Then the root of this subtree, which is 25, and then the right subtree, which being a single node now prints 27. And now that we are done with the green subtree, we visit the root of the red subtree, which is 33. And then traverse the right subtree shown within this green square. And because this is not a single node, we need to recursively traverse it in order. So the left subtree, which is 34, because this is a single node, then 39, and then 48. Alright. So now we have completely traversed the subtree surrounded with a red square. And now we visit the root, which is 52. And then traverse the right subtree, which we do recursively in order. So this is the sequence we would visit the nodes of a tree in order. The code for this is not very difficult, so I will just attach it for your reference, and you are expected to implement it yourself before looking at the solution. Another way of traversing a binary tree is to traverse it pre-order, in which case we first visit the root node, then we traverse the left subtree recursively in the pre-order way, and then the right subtree is traversed recursively the pre-order way. So if a tree had only 3 nodes, we would go to the root first, so let's print 52, then traverse the left subtree. But because it's a single node, we just print the value, which is 33, and then go to the right subtree, which again is just a single node, so we print 65. What about this example? We first visit the root, so let's print the data in the root node, then recursively traverse the left subtree, and finally traverse the right subtree. So when we get to the left subtree, we first visit the root, Because remember, whatever order we are traversing the main tree in, the same order needs to be applied for the subtrees also. Alright. So let's print 33. Then the left subtree within the red subtree, which we also traverse pre-order. So we print 25, then 12, then 27, then move to the right subtree and print it pre-order. So the root here, which is 39, then 34, and then 48. And then we move to the right subtree of the root. So 65, then 60, then this subtree. So 78, then 72, and finally 90. Post-order traversal is also very similar, just that the order of traversal is different. And in this case, we traverse the left subtree first, then the right subtree, and finally visit the root node. Similarly, if we are dealing with a more complex binary tree, a post-order traversal will look like this. We build a binary tree according to the data we get, right? So say we get some data from an array and we build a tree with that data by constantly doing insert operations. Now think about the case where the data that we get is ordered. That is, it is either in ascending or descending order. Let's take the example shown here. So we start with the first element, which is 5, and since this is the first element, it becomes the root, alright? Here we have the data in ascending order, right? So every time we insert an element, it will become the right child of the previous node, isn't it? We have 5 as a root element. Now the next element is 7, and since it is bigger than 5, it will become the right child of 5, right? And then we have 12. So 12 is bigger than 5 and also bigger than 7. So it will become the right child of 7. And each newly created node becomes the right child of the previous node. So if you look at it as a tree, it's not balanced. All the weight of the tree is on one side. It is pretty much like a linked list now. So if we were to search for an item, it will take order of n time, where n is the number of nodes. Alright? So the benefit of using the binary search tree data structure is lost now. A balanced tree is something like this. And the operations that we perform on a tree work well when we have a balanced tree. So ideally, we would want our trees to be balanced. But it's not possible to ensure that a general binary search tree will remain balanced because, well, that depends on the data that we get to build the tree, alright? But that said, there are techniques to keep binary trees balanced. There are different variations of balanced trees like AVL trees, red-black trees or B trees. But that is a slightly advanced topic and we'll not cover these in this course. For now, when analyzing algorithms on a binary search tree, we will assume it to be balanced. Now let's find the height of a binary tree, assuming that it is balanced. And by height of a tree, we basically mean how many layers does it have. So for example, this is a layer 1 which just has one node. Then this is layer 2 which has 2 nodes. Then layer 3 has 4 nodes and so on. So if we have h layers in a binary tree, we say that h is the height of that tree. And in the hth layer, we have 2 raised to the power of h minus 1 nodes, right? So in all, how many nodes do we have? Well, we have 1 plus 2 plus 4 plus so on, all the way up to 2 raised to the power of h minus 1. But now we need to find this height in terms of the total number of nodes, which is n. So we can write this expression. And the left hand side is just a geometric progression, right? And what is its sum? It is 2 raised to the power of h minus 1 divided by 2 minus 1. And this is equal to n. And from here we get h to be of the order of log base 2 of n. Alright. Now we come to the last part of this chapter, where we look at the time complexity of insert, delete and search operations on binary search trees. And of course, when we analyze these operations, we assume that the binary search tree is perfectly balanced. Alright. So let's start with searching for an item. Now, when we look for an item or some data, what do you think will happen in the worst case? Well, we always start from the root, right? And then based on whether the data to be found is greater than or less than the data at a node, we pick one of the children and check there until a node does not have any children, right? And that happens in the last layer of the tree where we have all the leaves, assuming we have a perfectly balanced tree. And the data could be present in one of those leaf nodes. So in each layer we do a comparison and then move on to the next layer. So in the worst case, we will be doing memory access proportional to the height of the tree, right? So we say that the worst case time complexity of finding an item in a binary search tree is of the order of log base 2 of n. Alright. What about deleting an item? Well, we first need to search for the item, right? Which, as already seen, takes order of log base 2 of n time. And we also need to make a few updates to some references after the delete. So essentially, the time taken to delete an item will be proportional to log base 2 of n plus some constant, which is big O of log base 2 of n. Similarly, for inserting the data in the right place, we keep comparing the data to the data held in a node until we find the right place for it to be inserted. And in the worst case, we may find that place in the last layer of the binary search tree. So the time taken for inserting an item into the binary search tree can also be said to belong to the big O of log base 2 of n. We have already seen some sorting algorithms. The basic sorting algorithms take order of n square time in the worst case to sort data of size n. Merge sort improves upon these algorithms and takes order of n log n time in the worst case. For any general unordered set of data, n log n algorithms are the best known ones for sorting. But because the constant factors in merge sort are a little high, it doesn't work very well for smaller sets of data. Now in this chapter, we will learn some more sorting algorithms, which take very interesting approaches to sort data. The first one is the quicksort algorithm, which is based on recursion techniques. Then we will learn the shell sort algorithm, which is basically an improved version of insertion sort. Then we will also learn about some linear time algorithms like counting, Redix and bucket sort. But these algorithms work for some specific kinds of data and they are not effective for any general data array. Now for this chapter, I will attach the source code at the right places, but we will not implement these algorithms during the lectures. The idea is to explain these using animations so that you get a feel of these algorithms. So let's start with the quicksort algorithm. The quicksort algorithm, as the name suggests, is a pretty fast algorithm. But in the worst case scenario, this algorithm takes order of n square time. And that's not good news. So why do we use it? Well, because it has been found that on an average, it takes order of n log n time, which is kind of as good as merge sort. And because the constant factors are smaller in case of quicksort, it performs better than merge sort in most cases. Another advantage that quicksort has over merge sort is quicksort can be done in place, that is without using any extra memory space, which is proportional to the data size. If you recall, in the merge sort algorithm, we used to create temporary arrays whose total size was equal to the size of the array to be sorted. So merge sort was not in place, alright? As long as we use a constant amount of temporary space, the sort is said to be in place. Even if we create 1,000 temporary variables while running an algorithm, that algorithm is still in place. Usually that does not happen, but still. But if the size of data is n and we need to use additional memory which is proportional to n, for example creating another array of size n or n by 2 or even n by a million, that is not in place algorithm, alright? So merge sort was not in place, but quicksort is. Let's get to the quicksort algorithm now. At the heart of this algorithm is the partition step. And what we do in this step is this. We select a number, any number in the array. But the convention is that we choose the last element of the array. This element that we choose is called the pivot element. After choosing this element, we rearrange the elements in the array such that the elements which are smaller than the pivot come to the left side of the pivot element, and all items larger than the pivot come to the right side of it. Notice that the parts of the array on the left and right of the pivot themselves may not be sorted. But the big idea here is that we can apply the quicksort algorithm to these left and right parts recursively, alright? Let's look at the pseudocode for the quicksort algorithm, which is very simple and straightforward. So let's say that the quicksort routine is written like this. It takes the array A as a parameter and the start and end index of the array to show which part of the array is quicksorted, because we will be doing it recursively, right? So the first time when it is called, we would have passed the array and the start index as 0 and the end index as the length of the array minus 1. So we check if the start index is less than the end index. Then we need to do something. And if it is not, which will happen when the start index will become equal to the end index, denoting we are dealing with a single element of the array. And that will be the breaking condition, because an array with single element is already sorted. This is quite similar to what we did in merge sort. So that should be easy to understand, I guess. So if a start is less than end, which means we are quick sorting part of the array which has more than one element, we first partition the array as explained earlier. And what is this pivot? Well, this is the index of the pivot element after the partition step is executed. Now understand this, before the partition step starts, we choose the last element of the array as the pivot, right? But after the partition step, the pivot element would have moved somewhere else in the array. So we want to know where the pivot element is now within the array, alright? So this pivot variable gives us the index of the pivot element after the partition step is done. After we know the pivot index, we can quicksort the left part of the array. So we say quicksort the array A from start to pivot minus 1 index, and then quicksort the right part of the array. So we say quicksort array A from pivot plus 1 index to the end, alright? And this is happening recursively. Make sure that you understand what the breaking condition here is. It will happen when start will become equal to n, and the method will not do anything but just return, alright? So the quicksort algorithm is quite simple. But what about the partition step? Let's understand that. Let's get to writing the pseudocode for the partition step. So we have this routine which will partition the array A from start to end. So as said earlier, let's choose the pivot element as the last element of the array. Then we initialize a variable I to the start value. So I will be used as an index, which at the beginning is here. Then we create another index variable j, which goes from I to end minus 1, like this. Alright. So it starts from I, and inside this loop we compare if element at j is less than or equal to the pivot element. And if it is, we exchange the elements at I and j indices, okay? And then increment I. So right now the value at j is not less than the pivot element, hence we just move j, because j is varying in the for loop. And now aj, which is 9, is less than the pivot element 10. Hence we exchange ai and aj, and then increment I. Then j moves ahead in the for loop, and again aj is less than the pivot. So ai and aj exchange places, and I is incremented by 1. And after the for loop has finished executing, we exchange ai with the pivot element itself, which is at the end, alright? So now all elements smaller than the pivot are on the left side, and all elements greater than the pivot are on the right side of it. And as you can see, the pivot element has come to the ith index. So we return I from this method, alright? The source code of the quicksort algorithm is attached, but I think the pseudocode is clear enough for you to try implementing it in Java or any other programming language of your choice. Let's study another very interesting sorting algorithm called shell sort, after the name of its inventor, Donald Shell. This algorithm is an improved insertion sort algorithm, but it can also be applied to bubble sort, but we will keep our discussion to the insertion sort, which is the main line. This algorithm works very well for medium-sized arrays, having elements up to a few thousands. Donald Shell saw a problem with the insertion sort algorithm and tried to fix it in his shell sort algorithm. And what is that problem? Well, if you recall, in case of insertion sort algorithm, we had to move a lot of elements to make place for the new element to be inserted in the sorted part of the array. And for large arrays, there would be a lot of element jumps, especially when we near the end of the array and the elements there are small. To understand, consider this example. We have this array and we start doing insertion sort on this, and after some iterations we are in this state. So the left part of the array is sorted, and now we come to the element 10, which will get inserted here in the sorted part, right? And to make space for this element, all these elements will have to move to the right, so that when this step is done, the array looks like this. And now the next element 9 is to be inserted at the right place. So most of the time is taken in moving the small elements to the beginning of the array, the jumps that they do, because essentially one such jump amounts to a whole bunch of elements moving to adjacent slots. So Donald Shell came up with a very innovative approach to solve this problem. And the intuition is that instead of trying to sort the whole array, we sort a part of the array, say every fifth element, and pretend that other elements do not exist. For example, in this array, we can just sort 25, 19 and 9. And after we are done, the data in the array looks like this, alright? And then we move to the next element. So now we can choose elements at index 1, 5 and 9 and pretend that other elements of the array do not exist, and just sort these 3 elements. So after sorting, the array would look like this. Then we move to the next set of elements, that is elements at index 2 and 6. So we keep the same gap between the elements, and after sorting each set, we move the index by 1. So now our first pass is over, and this is how the array looks like after the first pass. But as you can see, the array is not completely sorted. So in the next pass, we again start from element at index 0, but this time we reduce the gap between the elements. And we keep doing that until the gap between the elements is reduced to 1, which means that we will be sorting each element of the array. But the advantage would be that by that time, if there are smaller numbers towards the end of the array, they would have jumped to the starting of the array, and the larger ones would have moved to the end of the array. And that is advantageous because if the elements had to travel more distance within the array, they could do it in much lesser jumps. So that would be faster. And how do we choose the gap or interval between the elements? Well, we do that by using what is called as the Knuth sequence, which was formulated by Donald Knuth. And the number deciding what interval to use can be found by this recursive expression. So we would start by choosing the value of h as 1, and then the next value of h will be 4, and then 13, then 40, then 121, all the way up to a point where h is less than the length of the array. Because if we choose the interval to be more than the length of the array, the first element will be, of course, at index 0, and then the next element will not be within the array, right? Moreover, these intervals are chosen in the reverse order, and that is important to understand. We want the gaps or intervals to be large initially so that elements may quickly move across the array if they need to. And then we choose smaller and smaller intervals until we choose the value of h or the interval to be 1, which would be a regular sorting of the array. But by this time, the array would have already been sorted to a great extent. So if we have 100 elements in an array, the interval chosen for the first iteration will be 40, because according to Knuth sequence, we cannot use 121, right? That would not make sense. In the next iteration, we would choose an interval of 13, then 4, and finally 1. Let's understand with the help of an example. Consider an array of size 100. And it will be difficult to show all the elements of the array, so we will show only the relevant portions such that the shell sort algorithm is understood. If we have 100 elements, according to the Knuth sequence, the interval that we choose for the first time between the elements is 40. So this means that in the first pass of the first iteration, we will choose the elements at 0th index, 40th index, and 80th index, because the interval is 40. And then we will sort these 3 elements. That is, we sort of ignore all the elements for the time being. So after sorting these 3 elements, our array would look something like this. Then in the next pass of the first iteration, we will choose the adjacent elements. That is, elements at index 1, 41, and 81. So the interval is still 40, right? And sort these 3 elements. After which, this is how our array looks like. And then we move to the next index, still keeping the interval as 40, and sort these elements. So we will keep incrementing the index by 1 in each pass of this interval. That is, we will go index 0, 40, 80, then 1, 41, 81, then 2, 42, 82, and so on, up to 39 and 79, alright? So after the first iteration of the interval 40 is complete, this is how the array looks like now, alright? And now our second iteration starts. So we choose the interval to be 13. So in the first pass of this second iteration, we choose elements at 0, 13, 26, all the way up to index 91, and sort these elements. So let's assume that this is how the array looks like after sorting. Then in the next pass of this second iteration, we choose elements at index 1, 14, all the way up to index 92. After we are done with all the passes for interval 13, we do the same for interval 4 and then for 1, alright? That is, in the last iteration, we choose the interval as 1, which means that now we sort every element of the array. By the way, we commonly use insertion sort technique to sort array at each step, although we may choose another routine like bubble sort as well. We know that insertion sort algorithm on its own takes order of n square time. But it has been observed that on an average, when we use insertion sort with multiple passes as in shell sort, the time taken is much better than n square. It varies somewhere from n raised to the power of 7 by 6 to n raised to the power of 3 by 2. Alright? And this has been found using statistical methods. We have seen that for a general array in which the data is in a completely random order and there are no bounds on the data, the best algorithm that can be written will have a time complexity of the order of n log n. And merge sort is a pure n log n algorithm, while quicksort on an average has a worst case time of the order of n log n. Alright? But can we do better than that? Especially if we have some more information about the data. What if we know that however large the array itself is, each element can have a value between 0 and 10, let's say? Well, it turns out that if we have some kind of more information about the data, we can sort it in linear time. So in this chapter, we will learn about counting sort, Redix sort, and the bucket sort algorithms, which are all linear time algorithms. That is, they take time which is proportional to the data size. So let's start with counting sort. This is a very simple algorithm and is effective if the data is within some reasonable range. For example, if we know that the numbers in the array are between say 0 to 10 or 0 to 100, for example, marks given to a student in a test or exam. And you must have seen some teachers sort the papers like shown here, right? They kind of make piles of papers for each score or grade and keep fetching the papers from the common pile and sort, isn't it? So the counting sort algorithm is based on the same idea. So let's say we are given an array of n integers and we know that the integers vary from 0 to 10, say. So we can create a temporary array of this constant size 11 so that the array index varies from 0 to 10. And then we start reading the numbers in the data array. So first we read 3. So we increment the number at index 3 by 1 in the temporary array. Then we read the next number 10 and increment the count at index 10 by 1. And we keep doing this until we have read all the elements of the array, so that a temporary array looks like this. And now from this temporary array, we can recreate the original array but in the sorted order. So here the first element is 1. Then we have 3 2s, then 2 3s, and a 4, and so on. Alright? Easy? Now the time complexity of this algorithm is of the order of n. That is, it is a linear time algorithm. Let's see how we arrive at that. So in general, we assume that the data size is n, alright? And the range of numbers is within some number k, where k is reasonably small compared to n. Well, the numbers may even range from some k1 to k2, in which case we may use the idea of offset for array indices while counting the numbers into the temporary array, etc. Anyways, it's important to get the idea more than the details because details may be figured out later when you think about the variations. So when counting the numbers in the data array, we have to do n memory reads, isn't it? And then when we increase the counter in the temporary array, how many writes do we need to do? Well, there are n writes because every time we read a new number, we need to increment the counter in the temporary array. Then while constructing the sorted array, we have to do k plus 1 reads from the temporary array because k is the largest index of the array, isn't it? And then we do n writes to create the final sorted array. So the time taken will be proportional to the sum of all these individual times. That is, it will take time proportional to 3n plus k plus 1, right? And assuming that k is small compared to n, or even if k is of the order of n itself, we can say that the time taken by this algorithm in the worst case is of the order of n. Alright? Well, what happens if the data size is not huge? For example, let's say if the array size is 100 elements, but the elements inside may vary from 0 to 1000 or 0 to say 100,000. Would it be practical to use counting sort then? Well, these would be some practical considerations to be taken into account while designing your algorithms. Now, let's quickly understand what the Redix sort algorithm is. But before that, what is a Redix? Well, in a number system, the Redix or base represents the number of unique digits including 0 that are used to represent the numbers in that system. For example, in the decimal number system, the Redix or base is 10. In the binary number system, the Redix or base is 2. In case of Redix sort algorithm, we sort the numbers by the Redix position. For example, in case of decimal number system, we would first sort the numbers by digits in the ones place. Like in this example, if we sort the numbers just by digits in the ones place, this is how our array would look like. Then we move to the next position, the tens position, and sort all the numbers again based on the digit at the tens position, so that 713 will come first, then 821 and so on. And then we sort the numbers by digits in the hundreds position. And as you can see, all the numbers are sorted. Now, this algorithm is also a linear time algorithm because we go through all the numbers once in each iteration. And if there are k digits in the numbers, we would do k such iterations. So here in this example, we had 3 digits, so we had to do 3 iterations going over all the 6 numbers. So in all, we would do k times n memory access steps. So as long as k is not very large or is not proportional to n, it will take time proportional to k times n, and for small n constant k, that would be of the order of n. Alright? And to sort the numbers based on the digits at each step, we can just use counting sort, because the digits can only vary from 0 to 10 in case of decimal numbers. Redix sort works quite well at the bit level when the data is stored as ones and zeros. But extracting the digit from a number is an overhead. Plus, we also need to use additional memory, although additional memory may not be that big a deal. Now, let's come to the last sorting algorithm of this course, bucket sort, which is also known as bin sort. This algorithm takes a mixed approach from counting and Redix sort algorithms and works quite well for integers. So let's assume we have this array. And if you look at the data, the most significant digit in these numbers is at the hundreds position, right? So what we do in case of bucket sort is that we create this auxiliary array whose indices contain all the digits of the number system. Like here, we are dealing with the decimal number system, so we are using a 10 element array whose indices 0 to 9 cover all the digits of this number system. And we will look at the digit in the highest significant, and based on what digit it is, we will store that number at the appropriate index. So here we read the number 2, and the digit at its hundreds place is 0. So we store this number in the 0th index. Then the next number is 90, which also has a 0 at the hundreds position. So this also should be stored in the 0th index. But how do we do that? Well, we can simply use a linked list, right? So all numbers with 0 at the hundreds place can be stored in the 0th index of the array. Then we move to the next number, which has a 1 in the hundreds position. So we insert it at index 1 of the array. And we keep doing that for the whole array. Now that we have all the data laid out in this format, we again go to each array position one by one and sort the data in the linked list in each of these buckets or bins using any general sorting algorithm like, let's say, insertion sort. Alright. And then to lay out the sorted data in the source array, we start going over the auxiliary array again and just read all the nodes of the linked list data at each index and write it over to the source array. Alright. And that is quite simple. Now, what is the time complexity of this algorithm? Well, we have already said that it takes linear time, and that is the average time. But in the worst case, complexity still remains of the order of n square. Also, we get good running times if the data is evenly distributed across all the buckets. If most of the data clusters into one single bucket or slot, then sorting it will be essentially sorting one whole linked list itself. We will not get into a mathematically rigorous analysis which deals with how the data is distributed into various slots and the probability of the distribution, but as said earlier, it turns out that on an average this algorithm takes order of n time to sort the data. In this chapter, we will learn about the heap data structure and how are heaps used to implement priority queues. By the way, this heap is different than Java memory heap where objects are created. This heap here is a data structure, but in context of Java, we just mean a heap of memory or a pile of memory, alright? So what is a heap? Well, a heap is a binary tree, alright? So how is it different than a binary tree? And well, here I'm not saying binary search tree, okay? I'm saying a general binary tree. And you may want to recall the difference between the two here. So just as a binary search tree had some properties like left child is smaller than the parent and right child is greater than the parent, heaps also are binary trees with some special properties, okay? And the first one is that a heap is a binary tree that is complete. And what we mean by that is it is completely filled in when reading from left to right across each row, though the last row may not be completely full. This helps trees remain balanced, alright? So we get a dense tree with this property. For example, this tree is balanced, which means that each row is completely filled before we move on to the next row or the next level of the tree. And as said, the last row may not be full, which is fine. But in this example, this node's right child is missing, while the left child of its sibling is present. So if we go from left to right, there is a missing node right here. So this binary tree is not complete, hence it cannot be considered as a heap. But how do we make sure that a binary tree is complete so that it can be a heap? Well, that's simple. When we build a heap, we make sure that the nodes are inserted in a particular sequence. So if we already have this tree, it is complete as of now, and if a new node is to be added, it must be added as the left child of the leftmost node. And then another node should be added as the right child of the leftmost node, and so on. That is, at no point can we jump. That is, we cannot add a new node here. This will not be a heap. Rather, the node should be added as a child of this node first. Alright? So if we were building it from scratch, we start with the root. Then we add its left child. Then the right child. And then we add the new node as the left child of the root. And so on. Alright? So can we add a new node here? Well, no, because the layer above is still not complete. Alright? So the new node should be added here. Then another property of a heap is that every node's key or the data contained in the node is larger than or equal to the data contained in the child nodes. Alright? So this is a heap because if you consider any node, its key is greater than that of its children. And what about this? Well, this is not a heap because this node has a key 13, which is smaller than the key of its right child, alright? So now that we understand what a heap data structure is, let's see a few operations that we can do with it. Another common operation that we do in heaps is to delete the root element. This would usually be done in context of using the heap as priority queues, alright? So in this example, if we delete the root node, which node should become the root now? Of course, keeping the heap properties intact. Well, what we can do is that we first bring the last node in the heap to the place of the root, and then fix the heap by pushing it down so that it maintains the second heap property as well. So here 10 is smaller than both 15 and 12. So we exchange it with the larger node, which is 15. Then 10 is smaller than both 13 and 11. So we exchange it with 13, which is greater of the 13 and 11. And now the heap is fixed. So essentially, after moving the last node to the root, we keep checking if this node is smaller than its two children. And if it is, we exchange it with the larger of the two children. Alright? Now, what is the time complexity of deleting the root? Well, we have constant number of steps in putting the last node as the new root, because we will need to update a few references, right? And then for fixing the heap, the number of steps will be proportional to log n, because in the worst case, the node may have to travel from the root to the last level of the heap. So overall, it takes order of log n time to delete the root node of the heap. Let's see how to insert a new item or a new node into a heap. So keeping to the first heap property, that the heap should be complete, the only place that we can insert this node is to insert it as a left child of node 3, isn't it? Because the level at node 3 is completely full. But if we do that, it may break the second heap property, which is that each parent node should be greater than its children. So we need to bubble this new node upwards as long as its value is greater than the parent node. Alright? Let's have another node. This time we insert it as the right child of node 10, keeping the completeness property in mind. And then bubble this node because its value is greater than its parent. And we keep doing that until the second heap property is satisfied. So in this case, node 20 will go up and become the root of the heap, okay? We call this process of bubbling the new node as fixing the heap, alright? And what is the time complexity of fixing a heap? We already know that the number of layers in a binary tree are log base 2 of n. So in the worst case, the node may have to go from bottom to the top. So fixing the heap in the worst case would take order of log base 2 of n time. And how much time would it take to find the maximum element in a heap? Well, it takes constant time because the maximum element is right here at the root, okay? Because the largest element is always at the root node in a heap, the heap data structure may be used as a priority queue. Let's say that the keys at each node represent the priority of an item or node to be processed. Then the root element will always have the highest priority, isn't it? And once we are done processing the root node, we can delete it from the heap. And after we fix the heap, the node with the next higher priority will come to the root, right? So now that node may be processed. So using heaps as priority queues is really easy and straightforward. We don't need to do anything special. But sometimes in a priority queue, we change the priority of an item. That is, let's say that we change the key of an item or node. Let's consider this node 13. If we want to change the priority of this node to say 25, we can update the node value. But then we will need to fix the heap because 25 may be greater than its parent. So we may need to bubble this node up until it reaches the right place. That is, it is smaller than its parent node or has reached the root node. Let's take another example. Let's say we want to reduce the priority of 15 to 7. So we update the key in the node, and because the new node is lesser than the old one, we may need to push down the node to fix the heap, such that it reaches a place where its parent has a key greater than this node, and its children has keys lesser than this node, or it becomes a leaf node, alright? And changing the key in a priority queue which is implemented as a heap will take order of log n time in the worst case. So fixing the heap is a very important thing that we do in context of heaps, and it is used almost in all operations, whether it is inserting a new node or deleting the root element or changing or updating the key of a node. Now, how do we implement a heap? Of course, we can create a node object and then just create a binary tree like structure, just making sure that the heap properties are maintained, alright? But there is another way. We can use an array as an underlying data structure. And why does that work? Well, because if you look at a heap, the order in which the nodes are inserted can be marked as this, isn't it? I mean, considering that 0 is for the first node, 1 for the second, and so on. This is because we need to maintain the first heap property, which means that the heap should be complete. Now, if you look at any node and its immediate children, you can see a relationship. So if the parent is marked as I, its left child will be marked 2i plus 1, and its right child will be marked 2i plus 2, right? Now interestingly, the array indices also start from 0, and we can just represent the various nodes of the heap as elements of the array. For example, the root node may be held at index 0 of the array, its left child at index 1, right child at index 2, and so on. So this way of using arrays to represent heaps is very easy and effective. The implementation that we provide for inserting data in a heap and deleting the root node uses that array implementation. We will also keep using the array implementation for heaps in the lectures on heap sort. Now we'll look at the heap sort algorithm, which is another n log n algorithm. Let's say we have some data in the form of a heap data structure and we want to sort it. On the right hand side, we will display the array representation of the heap, alright? Now we know that the root is the largest element in the heap, and we would like to sort the data in the array in the ascending order. So what we can do is to exchange the root element with the last element of the array, alright? And because 20, which is the largest number, has reached the last index of the array, we can consider that part as sorted. And after doing this exchange, the heap needs to be fixed, which is just like the case of deleting the root node. So the node 10 has to be bubbled down until the second heap property is met. So now again, we have the largest number at the root, and we exchange this with the element at the second last index of the array, which is the second last element of the heap, right? So now the last two elements are sorted. And we again fix the heap. And we keep doing these steps repeatedly until all the elements are sorted. The heap sort algorithm takes n log n time in the worst case, because we swap n elements with the root, and after that we fix the heap, which takes log n time. Alright? But one issue with heap sort algorithm is that we usually get the data as arrays or lists. So to apply the heap sort algorithm, we need to first convert it to a heap, okay? And that's an overhead that takes additional time. Nevertheless, heap sort happens to be a very interesting algorithm. Let's see how to arrange some given numbers in a heap data structure. Let's say we are given this array of numbers, alright? And we would like to store them in another array of the same size, such that this new array represents a heap, okay? So let's start with the first element. The first element should become the root, right? So it should be placed at index 0, isn't it? So we place 8 at the root of the heap and move to the next number. Where should it be placed? Well, we first want to make the binary tree complete for it to be a heap. So we place this as the left child of the current root node. So this element will go to the index 1 of the array. And then we fix the heap. But because 3 is smaller than 8, the second heap property is satisfied, so we don't need to do anything in this case. Then we move to the next number 5. Where should we add it? To keep the tree complete, it should be added as a right child of the root node. So this would be added at index 2. So the idea of building the heap this way is that we keep putting the new numbers in the array in the increasing order of the index, starting from 0, then 1, then 2, and so on, and keep fixing the heap by moving the newly inserted element in the right place, such that the second heap property is satisfied. Alright? So here 5 is also less than the parent, hence we don't do anything and move to the next element, which is inserted at index 3. And now we need to satisfy the heap property. So the parent of element at index 3 is element at index 1. And if we compare their values, 7 is larger, so we swap these elements. And then compare element at index 1 and its parent. So 7 is smaller than 8 and the heap is fixed. So we move to the next element, which we insert at index 4. Then we fix the heap again. But because 2 is smaller than its parent, the heap is already fixed. Then we add the next element at index 5 and fix the heap. And we keep following this process until we have inserted all the elements. So the array on the right represents the same data, but as a heap data structure. The important thing to remember here is the relationship between the array index of the parent and its children, because we'll need that in our algorithm for comparing elements with their parents for fixing the heap. By the way, what is the time complexity for building a heap? It is big O of n log n, alright? because there are n elements to be inserted, and after inserting each element, we may take log n time to fix the heap in the worst case, alright? So a heap is quite an interesting data structure and works especially well for implementing priority queues. In this chapter, we will learn about hash tables. Hash tables are data structures which are great for very fast insertion and retrieval of data almost in constant time. You can imagine that the data structure looks something like this. It's just a collection of key and value pairs. The keys need not be just numbers, they can be any type of object. Similarly, value can also be any object that we would like to store, corresponding to a key. This value is known as satellite data. Think about a bakery which has these kind of regular items. And for each item and also the size, it may have created some kind of an identifier. Let's say it's just a number for simplicity. And if the records for all these items were to be stored in a computer, one may choose to use a hash table data structure to store these records. As you can see, an item contains information about which item it is, its size, and its price. So if a billing application was written, it will be very fast to access these records by the key, which is the ID of the item. Similarly, if we want to store users, we may choose to use their email addresses as the key, which will be of string type. And the value can be the corresponding user object. But how is it that we can access the values using their keys in constant time? Think about another data structure which gives us constant time insertion and retrieval of data. It is the array data structure which lets us do that. If we know the index of the element, then inserting and reading data at that index is a constant time operation, isn't it? So the trick is to use arrays as an underlying data structure. But the issue is that we can only use integer as keys because array indexes are integers. So let's see how a hash table is designed such that it is able to put any type of object as a key. So let's start with direct access tables. Direct access tables are very simple data structures which can store data in key value pair form. But it does not work in all the cases. It works only when the keys are integers, which are drawn from a set of m elements. Let's say a set of integers from 0 to m-1. Another assumption is that each of the keys that we use is unique. For example, no two records can have the same key value, alright? Now, this is very easy to implement. We just use a regular array of size m, so that its index ranges from 0 to m-1. And the index of the array can be used for the key, and the satellite data corresponding to that key may be stored at that particular index. Okay. So we can think of it that we have a set of distinct keys which may range from 0 to m-1, and the data associated with the key can be inserted or searched or deleted directly using the index of the array which is equal to that key. What about if the key set is very large? Well, then we'll need a very large array, right? Or even worse, what if the key data set is not very large, but the range of values is very large? For example, the number of keys may be, say, a few hundred, and they are distinct, but they may range from, say, 100 to a million. If we use an array of size million just to store a few hundred elements, that would be a huge wastage of space, isn't it? Another problem with direct access tables is that the keys must be integers. That is, we cannot use characters or strings or any other kind of object as a key, right? So to solve these kind of problems, we use what is known as hashing. Hashing is a way to map the keys of any type, it can be a string or any other object, to a random array index. Okay? Because if we can do it, then we will be able to store the data associated with that key into the corresponding array index. That's the big idea. And to do that, we use what is called as a hash function. A hash function is a function which maps keys randomly into slots of a table, which is represented by an array. Alright, so let's say we have a key k1, and if we apply the hash function on this key, we will get back an integer value, which can be used as an array index. We will see some pointers on how to implement some simple hashing techniques later, but for now, let's understand some ideas behind hashing. One thing to think about is what happens if we have a key which, when hashed, maps to a slot that has already been mapped and already contains some data. Where will we store the data associated with the new key now? So when a record to be inserted maps to an already occupied slot, we say that a collision has occurred. So does this make hashing useless? Well, not quite. There are ways to resolve collisions. And I wanted to think about what may be the simplest way to do that. One of the ways to resolve collisions can be not to insert the data directly into the array slot. Rather, we can use a list, a linked list kind of data structure for each slot. So even if multiple keys map to the same slot, the records can be stored as a linked list. Here each record contains the key as well as the satellite data in a node of a linked list. So if the hash function h, when applied to keys k2 and k3, evaluate to a single integer value I, we can store the data associated with keys k2 and k3 as a linked list at the same array index I. So this method of resolving collisions is called the method of chaining. Now, what would be the worst case time complexity of finding the item if we use chaining? Think about what will happen in the worst case. Well, in the worst case, all the keys may map to a single slot, right? That is, when we hash any key, we get the same value of the index where the record should be inserted. So all the records have been stored in one single linked list. So if you have to find the record associated with some key, say kj, the time complexity will be big O of n, right? Which is linear time. And that is not great, because our intention was to get the record in nearly constant time. So worst case is not good if we use chaining to resolve collisions. But what about the average case? Let's say in general we have n keys which need to map to m slots in the array, and we assume that hashing is uniform. That is, each key is equally likely to be hashed to any slot in the table, independent of where other keys are hashed. Or we can say that the hashing function is such that the hash values of all the keys are sort of evenly distributed across the slots of the table. In that case, in each slot, how many records will we have on an average? That will be n by m, right? Because there are n records evenly distributed in m slots, okay? So let's call this alpha. And this alpha is called the load factor. So if we need to find a record associated with some key, what will be the time complexity? It will be order of 1 plus alpha, right? This one is for the hash function call, assuming that the hash function call takes constant time. And alpha, the load factor, is the average length of the linked list in the chain. So is this a constant time operation? Well, in general it is not, because it depends on the load factor. So if the load factor is a constant, that is if n is some linear function of m, then alpha will become constant. And in that case, finding a record by its key in a hash table will become a constant time operation. So with changing n, m needs to keep up with it, at least by a constant factor. And if you care to look at the Java source file for the hash table or the hash map class in the java.util package inside the JDK, you will find that its capacity changes when we keep adding records into the hash table or the hash map, so that the load factor remains constant. Even if you take a look at the Java docs of HashMap, you will see references to capacity and load factor, alright? It's worth spending some time going through the Java docs at least. The default load factor that is used in a hash map, for example, as of Java 7, is 0.75. The main idea of hashing is that for any object which is acting as a key, we find some numeric representation of it and then hash it so that we can get to a slot in the array to be able to insert the data associated with that key. A good hash function should be able to distribute the keys uniformly into the slots of the array. And the keys themselves are natural numbers, possibly large natural numbers, which when hashed can map to an index of the array, alright? For example, if we want to hash this string, hash itself, we must first get to a natural number representation of it, alright? So how can we do that? Well, we can choose the ASCII values of each letter and then maybe add them up. But this won't be a great way to get to a natural number, because many character sequences may arrive at this same number, alright? Although we would like this number to be large and sort of unique. That is, at the minimum, there may not be many character sequences which may calculate to the same number, at least under reasonable assumptions. Another approach could be, because there are 128 unique ASCII characters, we can use 128 as kind of Redix and calculate the number by using the positional weight of the ASCII number associated with the character, alright? So this seems to be more reasonable than the first one. Anyways, so the first step is to get a natural number representation of the object, and that's why, if you may know, that we need to override the hash code method inside our Java class in case we need to use objects of our custom class as keys inside a set or a map, alright? So when we try to insert an object in a set or as a key, the first thing that Java does is to call the hash code method on that object, and then hashes the integer value returned into another integer, which can be used directly as an array index. Now, because the first step is to represent a key as a natural number, we will assume that the key is somehow represented as a natural number, which is then hashed into another natural number that maps directly into an array index. So let's say we have these keys 501 to 525 and we have an array of size 25, okay? So here n, which is the number of keys, is 25 and the array size m is also 25. One of the most simple hashing mechanism can be just to divide the key with the size of the array and return the remainder. So if we hash the key 501, the hash function would find the remainder of 501 divided by 25, which is 1. So the data associated with key 501 will go to index 1 in the array. And as you can see, calling this hash function is a constant time operation. Similarly, if we had to get the data corresponding to a key, we can hash the key again to find the index where the data could possibly be and just return the data in constant time. That's pretty cool, right? Now, this method of hashing is called the method of division, okay? It's kind of a quick and dirty way to hash, although there are better methods which are practically used in libraries out there. But we will discuss this method because it's quite easy to implement and it gives a fair idea about what hashing is about. So just like earlier, key 525 may be hashed to return 0. So that data associated with that key would be stored at index 0 of the array. Similarly, other keys may also be hashed. Now, what happens if we have more number of keys than the size of the array? Well, if we use the same strategy, we will get into cases of collision. Alright? But then we may use the method of chaining to resolve these collisions. Consider this case now. We have 13 keys ranging from 500 to 524, all even numbers, and they are to be hashed and stored in an array of size 12 or even 13, doesn't matter. Now if we hash the key 500, we get an 8. So we use index 8 to store the satellite data associated with key 500. Similarly, 502 can be hashed to give a value 10, and so on. And if you notice, keys 512 and 524 also hash to 8, right? So although the number of keys is about equal to the number of slots, the data will be placed in even numbered slots of the array, alright? That is at indices 0, 2, 4 and so on. And it's just because of the way the data is. Each of these slots getting a case of collision, but the odd numbered indices remain unused. Alright, so this is definitely not a great way for hashing. And even if you use this, heuristically we choose the size of the array to be a prime number, which is not close to a power of 2 or 10. But there are better methods than this one, like the method of multiplication, which we will not discuss here. The important thing is to understand what hashing is about using a simple method so that we are not bogged down by the details and complications of more realistic methods. You have already seen how to resolve collisions using chaining. In this lecture, we will learn another way to do that: open addressing. This method is used especially in context of those applications where one would not like to maintain a link to a list, or if we are not allowed to read the data of any other element in the list. So in this way, records are directly inserted in the array. Here in this array, I am showing the keys. Actually, the array will contain the satellite data associated with the key. But just to show that some value associated with a particular key is present in some slot, I am just showing the key itself, alright? So let's say we want to hash the key 256. So we hash it along with another argument. Let's say we start with a 0. This 0 is called the probe step. So first time we hash with a probe step of 0. And let's say that the hash value is 3. But we already have a record at index 3. So we hash again, but this time with a probe step as 1, alright? Let's say this hashes to 0. And again we have a record at that index in the table. So we hash again with a probe step of 2. And this time we get an empty slot. So we insert the record at this index in the array, okay? So this is the general idea of open addressing. Now open addressing requires that the number of keys should be less than the table size, because the table may fill up. And this is not a problem if we use chaining, because with open addressing, if the table gets full, we will keep probing and not get a place to insert the record. Another issue with open addressing is that deleting a record is not very straightforward, alright? Let's say a few records are already inserted in this array, and we delete the record at index 0, which has a key 321. But now if we want to delete the record associated with key 256, we will do a probe, hit index 3, but that's not key 256, so we probe again, going to index 0, But because this record was deleted earlier, we may think that the record for key 256 does not exist in this table. So there are tricks like not deleting the record actually, rather we can mark them as deleted. But it's not straightforward, alright? So delete is difficult in case of open addressing. There are many strategies for using open addressing, and we will discuss a couple of them here. One of the simplest ways is to use what is called as linear probing, alright? In this, we start from a base probe step, that is the probe step is 0, and we hit an index, say index 3 as shown here. If this index is already full, we just go to the next index, which is index 4. And if this index is full, we go to the next step. So we keep increasing the index linearly from the base index until we hit an empty slot, where we insert the record. So if we want to write this as an expression, we can write it like this. Hashing the key in probe step I is same as hashing it in the 0th probe step, which is the base, and then just add I to it. By the way, we can choose any other linear function of I rather than just I. But for the example, I is a good enough candidate for a linear function in I. Now, the problem with linear probing is there could be clustering of records in regions of hash table. And if that happens, then any key hashing into that region will have to keep looking for an empty slot to put the record, which will further increase the size of the local cluster. Because of that, one may choose to use quadratic probing. And in this case, instead of adding a linear function of the probe step to the base hash index, we can use a quadratic function. So that let's say that the base probe step finds 0 in the index, which is full. So the next probe step is probe step 1. Will add 1 square to the base index 0. Then the next step will add 2 square to index 0 and so on, until it finds an index having an empty slot. So if we were to write this in the form of an expression, quadratic probing may be expressed as this. And here, instead of just using I square, we may choose to use some other quadratic function of I, alright? Quadratic probing avoids clustering to some extent, but is not the best solution. The most practical of the approaches is what is known as double hashing, which may be expressed like this. Here we have two different hash functions, h1 and h2, which are calculated upfront for the key, and then the index is found by multiplying I, which is the probe step, to one of the hash functions and adding it to the other hash function, and then taking mod m of the whole. Statistically, it has been seen that double hashing works very well in distributing the keys evenly across the various slots of the table. Let's look at the time complexity for searching or inserting a record in a hash table using open addressing. And here our assumption is that hashing is uniform. And what that means mathematically is that if we have a hash function h and a hash table of size m, then the probability that two non-equal keys will hash to the same slot is 1 by m, alright? That is, any key being hashed to a slot is equally likely independent of the other keys which may already have been put into the table. With that assumption, in the worst case, the time complexity is clearly order of n. And why is that? Well, because in the worst case, we may have to go over each slot of the array or the table until we get the item we are looking for, or get an empty slot for the new record to be inserted. So the worst case is not very interesting. It's kind of bad. But on an average, hash tables are very fast data structures for inserting and finding items, alright? So that's what we'll discuss here, the average case time complexity. Now, the number of probe steps if we were using open addressing, is less than or equal to 1 by 1 minus alpha, if alpha is less than 1. And what is alpha? It's the load factor given by n over m, where n is the number of keys and m is the array size or the table size. So if the table size is more than the number of keys to be inserted, the number of probes will be less than this expression. And this can be found by using some mathematics, which I'll not talk about here. Essentially, we express the probability of inserting the record and add up those into an infinite geometric progression to get this expression. Well, for now, you can just take my word for it. That is the expression for the number of probe steps if alpha is less than 1. So if the table is 50% full, alpha is 0.5, right? And hence, number of probes to find an empty slot or to find a record associated with a key will also be less than or equal to 2. That's very fast. If alpha increases to 0.8, that is the table is 80% full, the number of probes in the worst case will now be 5. When it's 90% full, the number of probes will be less than or equal to 10. So the performance of inserting or reading a record drops as space utilization increases, and it drops really very fast. So essentially, for good performance, the hash table should never be too full. Okay? And if you see the Java source code for the hash table class in the JDK, they use alpha to be about 0.75 range. So hash tables in JDK operate at around 75% capacity. So here it's okay to waste some space to get better performance from your hash tables. Alright.